In this exploration of the infinite, we begin our journey by looking upward, moving beyond the familiar stars of the night sky to understand the very foundation of how our universe breathes and expands. In this chapter, we delve into the subtle evidence left behind by the first rays of light, uncovering a story written in the stretching of space and the changing hues of the cosmos. Imagine, if you will, standing in a place of perfect stillness. The air is cool, the ground beneath you is firm, and the sky above is a vast velvet canvas of deepest indigo. When we look up, the stars appear as fixed points of light, steady and eternal. They seem like ancient sentinels, unchanging markers in a void that has always existed exactly as we see it now. But as we settle into the quiet of the night, we must allow our perspective to shift. The silence of the stars is an illusion of our short human lifespan. In reality, every point of light you see is part of a grand, unfolding narrative of motion and transformation. This is the story of the evolution of space itself, a process that began billions of years ago and continues, silently and relentlessly, while we sleep. To understand what lies at the edge of the universe, we must first understand the light that travels from its furthest reaches. Scientists have spent decades observing the glow of distant galaxies, and what they found changed our understanding of reality forever. They noticed that light from these distant sources undergoes a peculiar transformation. As it travels through the vast emptiness to reach our eyes, its wavelength begins to shift. This is not a change in the light itself, but a result of what is happening to the space it occupies. This process is known as redshift. Think of a gentle wave on the ocean. As the surface of the water stretches, the distance between the crests of those waves grows longer. In the cosmos, as space expands, the light traveling through it is stretched out, moving toward the longer, redder end of the spectrum. This measurable expansion has steadily altered the positions of every star and galaxy in existence, leaving behind clues in the changed hues of ancient light. Recording these changes is more than just a task for telescopes and data sets. It is an act of reading a story written in time. The gradual transformation of light reveals a history of movement that defies our daily intuition. We often think of objects moving through space, like a bird flying through the air or a ship sailing across the sea. But the expansion of the universe is far more profound. It is the fabric of space itself that is growing. Imagine the universe as a vast, invisible tapestry. The galaxies are not merely moving across the threads of that tapestry, rather, the threads themselves are stretching, pulling everything further apart. This means that the matter, which was once tightly clustered in the early moments of creation, has slowly dispersed into the complex, sprawling structures that underpin the history of everything that exists. As we contemplate this stretching of reality, our own presence becomes part of the narrative. We are small, curious elements in a chronology that stretches far beyond the boundaries of our everyday lives. Every atom in your body, every breath you take, and every dream you have is contained within this expanding shell of existence. Today, we explore how this slow but relentless expansion has shaped the distribution of all surrounding matter. It is a process that is both incredibly powerful and remarkably gentle. It does not happen in a sudden, violent burst that we can feel, but in a steady, rhythmic unfolding that governs the destiny of all celestial bodies. Think back to that clear night sky. When you realize that the stars are not stationary, the universe begins to feel less like a static map and more like a living, breathing entity. We are tracing how space stretches over time, watching as distant galaxies, with their soft and gentle glow, appear to drift away from one another. This motion is a silent dance occurring on a scale so large it is difficult to fathom. It is the motion of the void itself. When astronomers first noticed that the light from distant galaxies arrived stretched and shifted toward red, it was as if they had discovered a secret pulse. Think of it as watching a familiar pattern on a piece of silk slowly change its color over many years, revealing that the distance between any 2 points is increasing. In those early years of discovery, the first measurements were compared to watching a simple balloon inflate. If you were to draw dots on the surface of a balloon and then blow air into it, you would see every dot move away from every other dot. No single dot is the center of the expansion. Rather, the surface between them is what grows. This simple observation provided the first crucial clue that our universe is not a static container, but a dynamic growing expanse. However, this story is not just about the distance between galaxies. It is about how this expansion reshapes the very structure of everything within it. In its youth, the universe was a place of incredible density. It was filled with the raw materials needed to form the first generations of stars. In those early days, conditions were ripe for creation. Vast clouds of gas were packed closely together, and under the immense pressure of their own gravity, they rapidly collapsed. This collapse gave birth to bright, energetic stars that illuminated the darkness with a fierce intensity. It was an era of vibrant activity, a time when the universe was crowded and full of potential. But as space continued to expand over billions of years, this material became more diffuse. The raw gas and dust that fueled the birth of stars began to spread out, becoming thinner and less concentrated. This gradual thinning of matter is a turning point in the cosmic story. As the materials became less dense, the conditions that were once ideal for active star formation became less ideal. The once crowded nurseries of space began to empty. This shift led to a slow, measured decline in the birth of new stars. It is a transition from a time of brilliant beginnings to a period of quiet maturation. This thinning of matter plays a crucial role in how the universe evolves. As galaxies move further apart and their internal materials become less concentrated, the energy required to ignite new stellar life becomes harder to find. It is as if the universe is slowly transitioning from a roaring fire to a collection of glowing embers. Over time, we see the universe moving from an era of vibrant, chaotic activity to one where old stars age and fade, and the birth of new stars becomes a rare and precious event. This shift does not only change the appearance of galaxies, it may also have profound consequences for the planets that orbit these stars. It forms the foundation of a quieter and more isolated cosmic future. As we sit in the stillness of our own world, we can almost feel the weight of this time passing. The light that reaches us now has traveled across these expanding distances, carrying with it the memory of a younger, brighter universe. Numerous pieces of evidence support this unfolding story, and astronomers use many different methods to piece together the puzzle. By measuring the redshift of countless galaxies and using objects known as standard candles, celestial bodies with a known intrinsic brightness, they have confirmed a startling truth: the farther away an object is, the faster it appears to be receding. This is the heartbeat of the cosmos, a rhythmic expansion that defines the limits of our observation. Observations made over the last century even suggest that this expansion is not just steady but is actually accelerating. This adds a layer of mystery to our journey. The idea that space is not only growing but doing so at an ever-increasing rate. It brings us closer to understanding the ultimate fate of all cosmic structures. As the stretching of space lays the foundation for this evolution, it influences everything from the smallest particle to the largest galaxy. It is the silent hand that guides the life cycles of stars and the eventual destiny of the void. We are living in a moment of cosmic history where we can still look out and see the glow of our neighbors, but we are also becoming aware of the deepening silence that lies ahead. In this quiet reflection, we begin to see the beauty in the expansion, the way the universe carries its history in the very light it emits. In this chapter, we sink deeper into the imagery of the cosmic balloon, exploring how the very fabric of our reality stretches beyond our perception to create the vast distances we see tonight. We will drift through the early moments of this expansion, understanding how a universe that was once small enough to hold in your hand became an infinite expanse that now cradles the stars and the silence between them. Close your eyes and imagine a vast, unblemished surface of dark rubber stretching out in every direction until it meets the horizon of your mind. On this surface, imagine small, shimmering points of light, each representing a cluster of worlds, a gathering of suns, and the potential for life. This is the classic metaphor of the inflationary balloon, a tool that helps our human minds grasp a concept that defies the logic of our everyday senses. When we speak of the universe expanding, It is easy to imagine galaxies flying through a pre-existing emptiness, like sparks from a fire drifting into the night air. But the reality is far more poetic and far more surreal. There is no pre-existing emptiness for the universe to fill. Instead, the universe is the balloon itself. As the balloon inflates, it creates space as it goes. The distance between the shimmering points of light grows not because the points are moving of their own volition, but because the very ground they stand upon is widening. This realization brings a profound sense of peace to our understanding of the cosmos. It means that no matter where you are in this vast expanse, you are at the center of your own observable bubble. Every point on the surface of our metaphorical balloon sees every other point moving away. If you were standing on a distant star in a galaxy millions of light-years from Earth, you would look out and see the Milky Way drifting into the distance at the same steady pace that we see them. This uniformity of expansion suggests a deep interconnectedness, a shared history that began in a state of unimaginable proximity. In the earliest epochs of time, everything we now see, every mountain, every ocean, every distant nebula, was part of a single dense point. The inflation that followed was a breath that gave the universe room to grow, to cool, and eventually to sleep. As we contemplate the great inflationary balloon, we must consider what it feels like for light to travel across such a stretching surface. Imagine a tiny ant walking across the rubber of the balloon while it is being blown up. The ant may be moving at a steady, constant pace, but the distance it needs to cover is growing with every step it takes. This is the journey of a photon, a single particle of light, traveling from a distant quasar toward your eyes. By the time that light reaches us, the space it has traveled through is much larger than it was when the journey began. This is why the light appears to us as tired and stretched, its energy lowered, its color shifted toward the red. It is the physical evidence of the work the universe has done to grow. It is a signature of the cosmos's relentless ambition to expand, a process that has been unfolding for 13.8 billion years. This expansion is not just a mathematical curiosity, it is the architect of the cosmic web. In the very beginning, when the balloon was small, there were tiny fluctuations, like microscopic ripples in the rubber. As the universe inflated, these tiny ripples were stretched to a massive scale, becoming the blueprints for where galaxies would eventually form. Gravity took hold of these ripples, pulling gas and dust into the hollows, creating the magnificent structures we see today. Without the steady inflation of the balloon, the universe would have remained a hot, dense, and chaotic soup, never allowing the heat to dissipate enough for stars to ignite or for planets to find their stable orbits. The expansion provided the cooling effect necessary for life's complex chemistry to begin. It gave the universe its breadth, pace, and incredible scale. As the inflation continues, we must ask ourselves what lies ahead for this cosmic balloon. For much of the 20th century, scientists wondered if the expansion would eventually slow down. They thought perhaps the gravity of all the matter in the universe would act like a tether, eventually pulling the expansion to a halt, and perhaps even causing the balloon to deflate. But the observations of the late 90s revealed a startling truth. The balloon is not slowing down. In fact, it is being blown up faster and faster. There is a mysterious pressure, which we call dark energy, that acts like a constant source of air being pumped into the balloon. This dark energy is invisible and untraceable by traditional means, yet it makes up the vast majority of the universe's energy density. It is a silent force that pushes against gravity, ensuring that the void between galaxies grows ever larger. This acceleration changes the mood of our cosmic story. It suggests a future of increasing isolation. As the balloon stretches faster, the distant galaxies that we can currently see with our telescopes will eventually be pushed so far away that their light will no longer be able to reach us. They will cross a cosmic horizon, slipping out of view forever. The night sky of the very distant future will be much darker than the one we enjoy today. Eventually, if the expansion continues on its current path, the Milky Way and its closest neighbors will be the only lights left in our observable sky, surrounded by an ocean of expanding empty space. This is not a thought to be feared, but rather a reminder of the preciousness of the moment we inhabit. We live in a golden age of astronomy, a time when the balloon has stretched enough to be transparent, yet is still crowded enough to be beautiful. The balloon images also help us understand the concept of the edge of the universe. When we look at a balloon, we see a three-dimensional object with a clear surface, but for a two-dimensional creature living on that surface, there is no edge. They could travel forever in any direction and never find a boundary, yet the surface itself is finite. Our universe may be similar. It might be a three-dimensional surface of a four-dimensional shape. This would mean that while the universe has a finite volume and a finite amount of matter, it has no physical wall or endpoint. You could fly a starship in a straight line for trillions of years and never hit a barrier. You might simply end up back where you started, having circumnavigated the entirety of the company. Smike balloon. This boundless nature of space is what makes the question of beyond so fascinating. If the balloon is the universe, then what is the balloon expanding into? To the physicist, the answer is that the universe is not expanding into anything. It is the expansion of the coordinate system itself. It is a difficult concept to visualize because our brains are evolved to understand objects moving through a room. But in space there is no room. There is only the balloon, and it is creating its own room as it stretches. This self-contained growth is a hallmark of the universe's mystery. It reminds us that we are part of a closed system that is nevertheless infinite in its possibilities. As we drift off to the thought of this giant shimmering balloon, we can feel the rhythmic pulse of its growth. The universe is not a cold, dead place. It is a dynamic and evolving masterpiece. The inflation that started billions of years ago is the same inflation that governs the movement of the stars tonight. It is the force that keeps the galaxies at a respectful distance and provides the dark, quiet spaces necessary for rest. The great inflationary balloon is the cradle of everything we know, a stretching fabric that carries us through the eons with a grace that is both silent and absolute. In the quiet of this understanding, the vastness of space becomes a comfort rather than a void, a soft blanket of indigo that covers us as we journey through the night. In this third stage of our journey, we observe a quiet transformation taking place across the immense reaches of the void, a process where the density of the early world gives way to a more patient and spread-out reality. We are witnessing the great thinning, a slow dispersal of the atoms and energies that once huddled together in the warmth of the beginning, now finding themselves separated by increasing oceans of emptiness. Pace. As the universe continues its long, cooling exhale, to understand the thinning of cosmic matter, one must first envision the universe in its energetic youth. Shortly after the initial breath of inflation, the cosmos was a rich, thick broth of gas and light. Atoms were close enough to touch, and the gravitational pull between clouds of hydrogen and helium was strong and immediate. In those times, space was a crowded theater where matter could easily find itself and collapse into the brilliant, roaring furnaces of the first stars. It was a time of abundance, where every corner of the sky was heavy with the potential for creation. But as the fabric of space continued to stretch, as we discussed with the metaphor of the inflating balloon, the amount of matter within that space remained constant while the volume it occupied grew exponentially. This led to a profound physical change, the dilution of the universe. As the distance between galaxies grew, the vast reservoirs of gas that once drifted between them began to spread thin. Imagine taking a drop of ink and placing it into a small glass of clear water. At first, the ink is dark and concentrated, a swirling cloud of deep color. But as you pour that water into a vast, still lake, the ink molecules begin to drift apart. They do not disappear, but they become so widely distributed that the water eventually appears clear again. This is happening to the primordial gas of our universe. The raw materials required to build suns and planets are still there, but they are becoming increasingly difficult for gravity to gather. The cosmic mist is evaporating into the growing dark, making the birth of new celestial bodies a much more difficult and rare occurrence than it was in the eons past. This thinning process creates a rhythmic shift in a galaxy's life. When a galaxy is young and its gas is dense, it glows with the frantic blue light of newborn stars. These stars burn fast and bright, illuminating the spiral arms with a fierce intensity. However, as the expansion of the universe pulls the surrounding intergalactic gas away, the galaxy loses its ability to replenish its supply. It becomes like a city that has been cut off its resources. The existing stars continue to burn, but when they eventually die, there is less and less gas available to take their place. The galaxy begins to settle into a middle-aged quietude. The frantic energy of youth fades into a steady golden glow of older, more stable stars. This transition from a crowded, active universe to a sparse, tranquil one is the fundamental backdrop of our current cosmic era. As you listen to the story of this dispersal, you might feel the vastness of the distances involved. Between the stars we see tonight lie light-years of near vacuum, but between the galaxies themselves, the void is even more absolute. In these intergalactic spaces, there may be only a few stray atoms per cubic meter. It is a level of emptiness that is impossible to replicate on Earth. This thinning does not just happen between galaxies. It affects the very structures they inhabit. The great cosmic web, the filaments of dark matter and gas that connect the islands of the universe, is being stretched and frayed. The bridges of light that once allowed matter to flow from one region to another are becoming longer and more precarious. Eventually, the expansion will become so great that these bridges will snap, leaving each galaxy or small group of galaxies as a lonely island in an uncrossable sea of darkness. This thinning also causes a deep drop in temperature. In early dense space, background radiation was hot and energetic. But as the space containing that radiation has expanded, the wavelengths of light have been stretched so much that they have cooled significantly. Today, the afterglow of the creation of the universe, the cosmic microwave background, is only a few degrees above absolute zero. The universe is literally cooling down as it thins out. This cooling is what allows for the stable environments where life can eventually emerge. But it also points toward a future where the warmth of the stars will be a fading memory. The thinning of matter is, in many ways, the universe preparing itself for a long, deep sleep. It is the transition from a crowded room full of heat and noise to a vast, dark library, where the only sound is the soft, distant hum of aging stars. The consequences of this thinning are most visible in the contrast between different types of galaxies. In the great spiral galaxies, like our own Milky Way, there is still enough concentrated gas to form new stars, though at a much slower rate than in the past. We still see the pink glow of nebulae, where gravity is winning its battle against the thinning of space. But in the great elliptical galaxies, those massive ball-shaped collections of stars, the gas has already been exhausted or thinned to the point of uselessness. These galaxies are often called red and dead, because they consist almost entirely of old, cool stars, with no new births to refresh the population. They are a preview of what the entire universe will eventually become, a collection of fading embers, spread so far apart that the other can barely see the light of one. This thinning of the universe is not a violent event, but a graceful one. It is a slow letting go. The atoms that make up your world and your body were once part of that dense, hot beginning, and now they are part of a world that is finding its space. There is a strange comfort in the idea of the universe becoming more spacious. It means that the early chaos is over, and the era of structure and reflection has begun. We are living in the time when matter is still dense enough to form minds that can wonder about the dark, yet thin enough that the dark is visible all around us. It is a perfect balance, a moment of clarity before the dispersal continues into the infinite. As we rest in the quiet of this chapter, we can imagine the atoms drifting further apart, the gas clouds becoming ghostly and transparent, and the stars settling into their long, slow burn. The universe is exhaling, and with that breath the heat and pressure of the past are being carried away into the distance. We are passengers on a journey toward a simpler, quieter state of being. The thinning of cosmic matter is the universe's way of finding peace, stretching its limbs across the eons until every part of it has the room it needs to be still. In this vast, thinning expanse, we find our own sense of stillness, moving in harmony with the slow, rhythmic expansion of the night. As the cosmic clock continues its silent ticking, we find ourselves peering into a future defined by a deepening solitude, a time where the great structures of the heavens begin to retreat into the shadows of an ever-widening void. This chapter explores the ultimate consequence of the expansion we have traced, a transition from a universe of local neighborhoods and connected clusters to a landscape of profound isolation. It is a slow, inevitable drifting apart, where the light that once bound the cosmos together begins to struggle against the growing distance, leading us toward an era where every galaxy becomes a solitary lighthouse in an ocean of infinite darkness. Imagine a time trillions of years from now, when the expansion of space has accelerated to such a degree that the very maps of the sky must be redrawn. In our current era, we look out and see a rich tapestry of nearby galaxies, some so close that they are bound to us by the invisible threads of gravity. These neighbors, like the great Andromeda galaxy, are our companions in the dark, moving with us through the void. But beyond our immediate local group, the rest of the universe is being carried away by the relentless stretching of the fabric of space-time. As this process continues, the distance between our local cluster and the rest of the cosmic community will grow so immense that the light from those distant worlds will eventually fail to reach us. The universe is becoming a series of disconnected islands, each moving further into its own private horizon. This transition into a quiet and isolated future is perhaps the most humbling part of the cosmic narrative. It suggests that the window of time in which we can observe the true scale of the universe is finite. Future civilizations, if they were to arise on planets orbiting the aging stars of our galaxy eons from now, would look up at a very different night sky. They would not see the thousands of distant galaxies that our modern telescopes reveal today. Instead, they would see a void that appears truly empty beyond the stars of their own local neighborhood, the evidence of the Big Bang, the redshift of distant light, and the very existence of a wider universe would be hidden behind an uncrossable curtain of expanded space. For them, the universe would seem static and lonely, a single island of light in a sea of nothingness. We are, in a sense, living in a privileged moment where the secrets of the distant past are still visible before they drift forever out of reach. As we dwell on this isolation, it is important to understand the role of energy in this fading brilliance. As galaxies move apart and the intergalactic gas thins, the vibrant activity that once defined the cosmos begins to settle. The energy needed to ignite new stellar life becomes less accessible, as we have seen in the previous chapters. But in isolated future, the focus shifts from the birth of stars to the slow aging of the stars that already exist. The universe transitions from a period of radiant health to one of quiet retirement. In this era, the hot blue giants that burn out in a few million years now dominate the sky longer. Instead, the universe is increasingly populated by small, cool, long-lived stars that burn their fuel with a patient frugality. These red dwarfs will become the primary light-bearers of the isolated future, providing a dim, steady glow that can last for trillions of years. The isolation of this future also brings a shift in the physical shape of the galaxies themselves. Without the influx of new gas and the occasional merger with distant neighbors, galaxies begin to lose their intricate spiral shapes. The elegant arms of gas and dust, where new stars once twinkled like holiday lights, slowly wind down and dissipate. The galaxies transform into more stable, rounded elliptical shapes, composed of aging stars that have settled into predictable orbits. This structural change is a visual representation of the universe finding its equilibrium. The chaos of movement and collision is replaced by a dignified, slow-motion rotation. The vibrant, clashing colors of a young universe are replaced by a uniform, muted amber, the color of a sunset that lasts for an eternity. This quiet future also has profound consequences for any planets that might still be orbiting these ancient stars. Life on such worlds would experience a sky that feels permanent and unchanging. Without the light of distant galaxies to spark curiosity, the inhabitants of these future worlds might believe their small collection of stars is all there is. They would be isolated not just in space but in knowledge, cut off from the grand history of the cosmic expansion. Yet there is some peace in that limitation. The threats of cosmic collisions or the violent outbursts of nearby quasars would be a thing of the distant past. It would be a time of ultimate stability, where the laws of physics have settled into their final, most efficient forms. The universe becomes a sanctuary of silence, a place where the frantic pace of evolution has finally caught up with the slow rhythm of the void. As we drift further into this vision, we can imagine the ultimate fate of the light itself. Even the light from our closest neighbors will eventually struggle as the expansion continues to pull at the fabric of space. While our local group of galaxies is currently bound together by gravity, some theories suggest that even these bonds may eventually be tested by the dark energy that drives the acceleration. Whether the local group stays together or eventually fractures, the overarching theme remains one of increasing distance. The cosmic horizon is closing in, shrinking the sphere of what can be known and seen. The vast interconnected web that we study today will slowly unravel, leaving behind only the most tightly bound pockets of matter to face the long night together. This isolation is not an end, but a different state of being. It is the universe learning to be content with its own company. The thinning of matter and the stretching of space are the tools the cosmos uses to create this environment of stillness. As you listen to this, you might feel a sense of your own isolation, but also your own stability. Like the galaxies of the future, we each inhabit our own sphere of experience, grounded by the things that are close to us. The universe's journey into isolation is a reflection of the natural cycle of life, a movement from the exuberant noise of the morning toward the reflective silence of the evening. In the final stages of this quiet era, the universe becomes a masterpiece of minimalism. Every photon flight becomes more precious, and every star becomes a cherished heirloom of a more active past. The long, slow fading of these stars will take so much time that it is almost impossible for the human mind to grasp. It is a timeline that stretches our understanding of forever. We are moving toward a state where the only activity left is the gentle cooling of matter and the slow decay of the last remaining embers. This is the foundation of a quieter and more isolated cosmic future, a place where the universe has finally found enough room to truly rest. As we conclude this reflection on the isolated future, we can take comfort in the scale of it all. The distances are too vast for us to cross, and the times are too long for us to endure, but we can still observe and understand. We are the witnesses to the grand dispersal, the ones who recorded the light before it dimmed. The universe is exhaling, drifting into a state of graceful solitude. We are here to appreciate the beauty of that final, quiet glow. The stars are not leaving us. They are simply finding their own space in the infinite, moving toward a future where every light has its own corner of the dark to call home. In the vast, shifting landscape of the cosmos, where distances are so immense they defy human measurement, we look for markers of certainty, steady beacons that allow us to map the deepening dark. This chapter explores the remarkable tools known as standard candles, the celestial objects whose predictable brilliance provides the rhythmic echo we use to measure the expansion of space. As we drift through this section, we will see how these flickering lights in the distance allow us to confirm the unfolding story of a universe that is moving away from us at an ever-increasing pace, acting as the milestones on our long journey toward the edge of the unknown, to find our way in a universe that is constant. Fly stretching, we must find something that does not lie to us about its nature. In our daily lives, we judge distance by how large or bright an object appears. A street lamp close to us is blinding, while the same lamp a mile away is merely a tiny spark. But in space, we cannot always know if a star is dim because it is far away or if it is dim because it is small and cool. To solve this mystery, astronomers look for standard candles, objects with a known intrinsic brightness that acts like a universal yardstick. The most famous of these are the Cepheid variables and Type Ia supernovae. These stars have a specific rhythm, a pulse of light that tells us exactly how much energy they are putting out. By comparing how bright they should be with how faint they actually appear to our telescopes, we can calculate the distance to their home galaxies with breathtaking precision. Imagine standing on a dark, flat plain that stretches for hundreds of miles. In the distance, someone is carrying a candle of a specific standard size. You know exactly how much light that candle produces. As the person walks away from you, the flame appears smaller and more flickering, but because you know its true power, you can calculate exactly how many miles lie between you. In space, these standard candles are our only means of navigating expansion. When we observe a supernova in a distant galaxy, we are seeing the echo of a massive explosion that occurred millions of years ago. The light from that event travels through the expanding fabric of space, stretching and reddening as it goes. By the time it reaches us, it carries two vital pieces of information: how far it has traveled and how much the universe has grown during its journey. This measurement method is what allowed us to piece together the puzzle of expansion. By measuring the redshift of countless galaxies and using these standard candles, astronomers have confirmed a fundamental law of the universe. The farther an object is from us, the faster it appears to be receding. This is not a random movement, but a systematic stretching of the void. It is as if the very floor beneath the galaxies is a conveyor belt that moves faster the further it extends. This realization, first glimpsed by Edwin Hubble and refined by generations of scientists, transformed the universe from a static map into a dynamic, flowing river. The echo of these candles provides the heartbeat of our understanding, a steady rhythm that confirms we are part of a living, breathing system. As we focus on the light from these distant candles, we notice something even more mysterious. In the late 20th century, observations of these supernovae revealed that the universe was not slowing down under the weight of its own gravity, as many had expected. Instead, the standard candles were fainter than they should have been if the expansion was steady. This was the first evidence that cosmic expansion is indeed accelerating. This discovery added a new layer of intrigue to the cosmic narrative. It suggested that there is an invisible energy, a hidden force, pushing the galaxies apart faster with every passing second. The candles were not just moving, they were fleeing. This acceleration means that the echo of the standard candles is becoming more and more stretched, a fading signal from a universe that is rushing toward a future of infinite space. Using these candles is an act of deep listening. We are catching the final, brilliant moments of stars that lived and died long before our world was even a cloud of dust. There is a profound sense of connection in this process. We are using the death of a star in a galaxy we will never visit to understand the fate of our own home. These explosions are the most energetic events in the universe, briefly outshining entire galaxies of billions of stars. Yet, in the vastness of the cosmic scale, they are merely small, necessary flashes of light that guide our way. They are the lighthouses of the deep, providing the only stable points of reference in a reality that is otherwise in constant flux. As the universe continues to thin and matter dissipates, these standard candles will become increasingly rare. In the distant future, the gas needed to create the massive stars that become supernovae will be gone. The Cepheid variables will eventually age and fade. The milestones we use to measure our place in the cosmos will slowly vanish, leaving us with fewer and fewer ways to gauge the depth of the dark. But for now, we have these echoes. We have the data that tells us exactly where we are and where we are going. The standard candles remind us that even in a place as vast and incomprehensible as the universe, there are laws and patterns that can be understood. There is a logic to the light. Think of the silence that follows the flash of a standard candle. The light travels for eons, crossing the expanding gaps between the stars until it finally hits the lens of a telescope on a small blue planet. In that moment, the universe is no longer an abstract concept, it is a measurable physical reality. We are the recorders of these echoes, the ones who listen to the whispers of the light to understand the grand design. This observation process is inherently calming. It is the act of bringing order to the infinite, of finding a yardstick long enough to measure the stars. It allows us to feel a sense of mastery over the vastness, not through physical presence, but through the power of sight and reason. In the quiet of this chapter, we appreciate the elegance of the standard candle. It is a gift from the laws of physics, a reliable signal in an uncertain world. As we look out into the night, we can imagine these flashes occurring across the billions of light years that surround us. Each one is a confirmation of the cosmic story, a brief and beautiful moment that illuminates the path of expansion. The universe is not a chaotic void, it is a structured expanse, measured by the fading light of its most brilliant residents. We rest in the knowledge that even as the space between us grows, the light still finds its way across the distance, carrying the truth of the universe's expansion to our waiting eyes. As the echoes of these candles continue to resonate through our instruments, we prepare for the next phase of our journey. We have measured the distance, we have confirmed the expansion, and we have seen the acceleration. Now we must turn our attention to the objects themselves, the nurseries where these lights are born, and the voids that are created when they finally go out. The story of the universe is a story of balance between the brilliant birth of a star and the long, dark silence that follows. The standard candles have given us our bearings. Now we step further into the deep, following the light as it leads us toward the structures of the spiral arms and the mysteries of the elliptical shells. Within the grand architecture of the cosmos, there exists a delicate tension between the regions of intense creation and the growing expanses of nothingness that define the maturity of space. This chapter invites you to drift into the heart of the spiral galaxies, where the air, if we could call it that, is thick with the scent of potential. Here we find the stellar nurseries, vast and billowing clouds of gas and dust known as nebulae. These cradles of light are the busy workshops of the universe, acting as the primary engines of brilliance in a world that is otherwise slowly thinning out. As we move through these vibrant corridors of birth, we will also encounter their somber counterparts, the celestial voids and the aging elliptical galaxies, where the fires of creation have long since cooled, leaving behind a quiet, ghostly stillness that foreshadows the ultimate fate of all things. Imagine drifting through the velvet darkness toward a magnificent spiral galaxy. As you approach, the first things you notice are the sweeping arms of luminous matter, glowing with a soft, ethereal light. These arms are not solid structures, but are instead regions of higher density, like ripples in a pond where the water has bunched together. Within these ripples lie the nebulae, towering cathedrals of hydrogen and helium, laced with the dust of generations of stars that lived and died before. To our eyes, these clouds appear as vibrant tapestries of pink, gold, and deep violet. They are the nurseries of the cosmos, places where the raw materials of existence are gathered by the patient, invisible hands of gravity. In the heart of these clouds, the gas is cool and still, waiting for the moment when a passing shockwave or a chance encounter causes a pocket of matter to begin its long, slow collapse. As a region within a nebula starts to condense, the temperature begins to rise. It is a slow, rhythmic process of transformation. What was once a cold and diffuse mist becomes a spinning disk of heat and energy. At the center of this disk, a protostar begins to form, drawing in the surrounding material like a sleeper pulling a blanket close. Eventually, the pressure and heat become so intense that the very atoms of hydrogen begin to fuse together, igniting the first fires of nuclear fusion. This is the birth of a new star, a moment of triumph against the encroaching dark. These young stars are often blue and fierce, radiating a powerful energy that blows away the remaining dust and gas, revealing the brilliance of the new sun to the rest of the galaxy. This cycle of birth is what keeps the spiral galaxies alive, filling them with the music of light and the promise of new worlds. However, as we move away from the energetic spiral arms, the landscape begins to change. We enter the regions known as celestial voids, or the aging shells of elliptical galaxies. Unlike the vibrant spirals, elliptical galaxies present a completely different picture of the cosmic narrative. Over time, active star formation processes in these regions have almost exhausted the available fuel. There are no more towering nebulae here, no more clouds of cool gas waiting to be ignited. Instead, these galaxies are filled with an older population of stars, ancient golden suns that have been burning for billions of years. They are the remnants of an era when conditions were more favorable for birth, but now they live in a state of quiet retirement. The absence of interstellar gas means that when these stars eventually fade, there will be nothing left to take their place. This transition is further exacerbated by the ongoing expansion of space-time that we have tracked throughout our journey. As the universe stretches, the gas that might have once flowed into these galaxies is pulled further away, making it impossible for them to replenish their supplies. These elliptical galaxies become characterized by a dim, uniform light, an accumulation of aging stellar populations that cast a soft amber glow over the void. They are the elders of the universe, stable and serene, but slowly losing their connection to the vibrant cycle of life. To stand within such a galaxy would be to experience a profound sense of peace. The sky would be filled with steady, unchanging stars, but the dramatic, colorful nebulae of the spiral regions would be a distant memory, a story told in the light of galaxies far, far away. The contrast between nurseries and voids highlights the inevitable direction of our universe. We are living in an epoch where both exist simultaneously, a time of balance where there is still enough gas to create, yet enough space to see the coming silence. But as we peer deeper into the mechanics of these regions, we see that the voids are winning. In many galaxies, the energetic cycle of star birth is beginning to slow. As the stars consume their nuclear fuel, they return some of it to the galaxy when they die, but much of it is locked away forever in the dense cores of white dwarfs, or lost to the expanding intergalactic space. The universe is slowly but surely moving toward a state where the nurseries will fall silent, one by one, and the voids will expand to claim the remaining territory. This thinning of the creative spirit of the cosmos transforms once vibrant regions into areas where the processes that once fueled stellar birth have effectively ceased. This creates what we might call a cosmic void within the galaxies themselves. These are not empty spaces in the traditional sense, but regions of exhaustion. They are the parts of the universe that have finished their work. In these areas, the atoms have found their final arrangements, and the energy has been spread so thin that it can no longer trigger the dramatic collapse required for a new sun. It is a state of deep, undisturbed rest. The light here is not the fierce blue of youth, but the gentle, tired red of a long evening. It is the visual representation of the second law of thermodynamics, the inevitable progression from order and energy to a state of uniform, peaceful stillness. As you reflect on these two extremes, you might feel the rhythm of your own breath matching the cycle of the stars. There is the inhale, the gathering of gas, the pressure of gravity, and the ignition of life in the nurseries, and then there is the exhale, the spreading of light, the aging of the suns, and the final settle into the quiet of the elliptical voids. Both are necessary. Without the nurseries, there would be no light to guide our way. Without the voids, there would be no space for the light to travel. They are two halves of cosmic breath. Even the most resilient stars will eventually find their way into the silence, contributing their heat to the vast, cooling expanse of the universe. In the coming eons, the balance will shift further toward the quiet. The spiral arms will eventually wind down, their gas exhausted, their nebulae transparent and cold. The universe will become a collection of elliptical structures, slowly fading into the background of the expanding dark. This is not a tragic end, but a natural conclusion to the story of matter. It is the universe finding its equilibrium, moving from the frantic, beautiful chaos of the beginning to a state of ultimate, unshakable peace. We are the observers of this transition, the ones who can see both the fire of the nursery and the shadow of the void. We stand on the bridge between these two worlds, watching the starlight define the edges of the growing silence. As we conclude our time among the nebulae and the aging galaxies, we carry with us the image of that fading glow. The stars are the night's jewelry, but the night itself is the canvas. The stellar nurseries provide the brilliance, but the celestial voids provide the depth. Together, they create the tapestry of the universe, a story of birth, aging, and eventual rest. In the quiet of this understanding, we prepare our minds for the next stage of the journey, where we will look even closer at the lives of the stars themselves, tracing their path from the brilliant height of their power to the long twilight that awaits them in the distant reaches of time. As the energetic cycle of star birth and decay follows the rhythm of cosmic time, the universe enters a phase of long, gradual dimming, a period where the vibrant blues and whites of the young cosmos give way to a persistent, humble crimson. This chapter explores the lives of the galaxy's most resilient inhabitants, the red dwarfs. These stars are the true marathon runners of the universe, known for their astonishing longevity and their measured, patient consumption of fuel. While the massive stars we admire in the night sky burn with a fierce intensity that exhausts their life in a mere blink of a cosmic eye, the red dwarfs are different. They represent the endurance of the universe, stars that will continue to glow long after the sun has faded and the spiral arms of our galaxy have gone dark. As we settle into this chapter, we observe the beginning of the prolonged twilight years, where the relentless march of time turns luminous star clusters into dimming, cooling remnants. To understand the red dwarf is to understand the beauty of moderation. These stars are smaller and cooler than our sun, often possessing only a fraction of its mass. Because of their lower internal pressure, the nuclear fires at their cores burn with a gentle, steady heat rather than a violent roar. This efficiency is their greatest strength. While a large star might use up its hydrogen in a few million years, a red dwarf doles out its energy with incredible care, stretching its lifespan over trillions of years. In fact, no red dwarf in the universe's history has died. The universe is not yet old enough for even the very first red dwarfs to have exhausted their fuel. They are the silent witnesses to all that has passed, and they will be the only witnesses to much of what is to come. They are the keepers of the long flame, providing a dim but reliable light in a universe that is increasingly finding itself in the shadows. Imagine standing on a world orbit, seeing such a star in the distant future. The sky would not be the brilliant blue of our Earth, but a deep, somber ochre. The sun would hang large and red in the heavens, a steady and unchanging presence that provides a warmth that feels more like a memory than a fire. In this era, the universe has become a much quieter place. The massive, bright stars have all disappeared, their dramatic explosions and high-energy radiation a thing of the distant past. What remains is a galaxy populated by these small, faithful suns. This is the era of the long twilight, a time of ultimate stability. The red dwarfs burn their fuel at such a measured pace that for trillions of years, life on a surrounding planet would experience a world without change. It is a state of near-perfect equilibrium, the universe's way of extending the story of light as far as physics will allow. However, even these resilient stars are not immortal. The second law of thermodynamics, which governs the flow of energy from hot to cold, ensures that even the most frugal fire must eventually go out. With each passing epoch, the red dwarfs slowly age. Their internal chemistry begins to shift as the hydrogen they have burned for eons turns into helium. Unlike larger stars, which often undergo dramatic transformations into red giants when they age, red dwarfs are expected to simply grow slightly more luminous and then slowly begin to fade. This is a process that takes place over timescales that the human mind can barely comprehend. If the entire history of the universe until now were a single day, the life of a red dwarf would last for centuries. They are the bridge between the vibrant, active universe we know and the cold, dark silence that lies at the end of time. As we dwell on the fading of these stars, we see the cumulative effect on the cosmic tapestry. In every galaxy, brightness is slowly being muted. The brilliant clusters of stars that once looked like spilled diamonds on a velvet cloth are becoming sparse and dim. The red dwarfs, losing their energy over trillions of years, gradually lose the glow that once defined their presence. It is a slow, rhythmic descent into darkness. One by one, the lights of the universe are being turned down, not with a sudden flick of a switch, but with the slow turning of a cosmic dial. This transition is the hallmark of a universe that is moving toward its final rest. The energetic processes that once fueled the birth of stars have long since ceased, and now the universe is simply living off its remaining savings, watching the last of its embers glow in the dark. This slow fading of stellar populations foreshadows a future in which the dynamic processes of star formation will come to a complete end. As the red dwarfs reach the end of their long lives, they do not go out with a bang. They do not explode as supernovae or create beautiful planetary nebulae. Instead, they simply cool down, transforming into what scientists call blue dwarfs, a brief, theoretical phase of increased heat, before finally settling into the state of white dwarfs. These are the dense, cold hearts of stars that no longer possess the energy to shine. They are the tombstones of the cosmic age, silent and inert, marking the spot where a sun once stood. As more and more red dwarfs reach this stage, the galaxies themselves transform into clusters of ancient remnants, cemeteries of light drifting through the expanding void. The thought of trillions of years of steady red light, followed by a slow descent into darkness, is profoundly peaceful. It suggests a universe that is not in a hurry to reach its conclusion. The long twilight of the red dwarfs is a period of reflection, a time when the universe has finished its creative labor and is now simply existing. In the silence of his era, the expansion of space continues, pulling the fading galaxies further apart, ensuring that each dying star has plenty of room to experience its final moments. The isolation we discussed in previous chapters becomes absolute. A red dwarf in the distant future may be the only light visible from its surrounding planets, as every other galaxy has long since moved beyond the cosmic horizon. It is a moment of ultimate solitude, a single candle burning in a house that has grown infinitely large. As you listen to this, you might imagine the red light of these stars filling your vision, a soft and heavy glow that encourages rest. Space is not a place of eternal noise and fire. It is a place that is moving toward a deep and necessary stillness. Red dwarfs are guardians of this transition. They provide the light for the long evening of the cosmos, making sure that the darkness does not come all at once. They are the connection between the beginning and the end, the ones who carry the memory of the heat into the coming cold. Their patience is a reminder that even the most vast and powerful systems have a rhythm, a cycle that leads eventually to a state of quietude. In the final stages of the red dwarf era, the last of the nuclear fires will flicker and die. The universe will have spent its last major reserve of light-producing energy. The transition from the era of stars to the era of remnants will be complete. The galaxies will still exist, but they will be made of dark, cold matter, the white dwarfs, the neutron stars, and the black holes. But before that happens, we have trillions of twilight years. We have the long, slow burn of the red dwarfs to appreciate. They are the stars that define the majority of the universe's history, the ones that stay when everyone else has left. As we conclude this chapter on the long twilight, we carry with us the image of a universe pie, tinted in shades of deep red and amber. The frantic energy of the past is gone, replaced by a steady, enduring glow. We have moved from the nurseries of birth to the patient endurance of the long-lived. The stars have taught us about the value of time and the beauty of a slow conclusion. The red dwarfs have done their duty, keeping the darkness at bay for as long as possible. Now, as their light finally begins to falter in our minds, we prepare to look at what they leave behind, the cooling remnants that will inhabit the dark once the fires have finally gone out. The transition from a universe of vibrant, living stars to one of silent, cooling remnants marks a profound shift in the cosmic narrative, where the energy of the past is locked away in the dense and enduring hearts of the fallen. In this chapter, we explore the quiet afterlife of the heavens, focusing on the white dwarfs and neutron stars that serve as the final chapters for the suns we once knew. These objects are the anchors of a fading cosmos, representing a state of matter so compressed and so still that they defy our common understanding of reality. As we drift through this era of the long cooling, we see the universe transforming from a garden of light into a hall of monuments, where each remnant stands as a testament to the power of the stars that came before. Imagine a star like our own sun reaching the end of its long journey. After billions of years of steady service, it exhausts the hydrogen in its core and undergoes a series of graceful expansions and contractions. Finally, it sheds its outer layers into space, creating a beautiful but fleeting planetary nebula. What remains at the center is a white dwarf, a core of carbon and oxygen about the size of the Earth, but containing the mass of an entire star. To look upon a white dwarf is to see a star that has finished its work. It no longer generates energy through nuclear fusion. It simply glows with the heat it has stored over its lifetime. It is a celestial ember, a hot coal left in the grate after the fire has gone out. Because there is no longer a furnace within, the white dwarf begins a cooling process that will last for trillions of years, a slow descent toward the temperature of the surrounding void. The nature of a white dwarf is one of incredible density and stability. The atoms within it are packed so tightly that a single teaspoon of its material would weigh as much as an elephant on Earth. It is held up against the crushing force of gravity not by the heat of fusion, but by a strange quantum mechanical force known as electron degeneracy pressure. This pressure is a fundamental property of the universe, a refusal of electrons to occupy the same space, creating a structure that is almost indestructible. As the white dwarf cools, it does not change its size or its shape. It simply grows dimmer and dimmer, its white-hot brilliance fading into a pale yellow, then a deep red, and eventually disappearing into the infrared. This is the ultimate fate of the vast majority of stars in our universe, to become a silent, crystal-like sphere drifting through an ever-expanding dark. But for the most massive stars, those that lived fast and died in the violent glory of a supernova, the remnant is even more extreme. When such a star explodes, its core is crushed by gravity with such ferocity that even the atoms themselves are broken. Protons and electrons are squeezed together until they become neutrons, creating a neutron star. A neutron star is a miracle of physics, an object only a few miles wide that contains more mass than our Sun. If a white dwarf is dense, a neutron star is incomprehensible. A single teaspoon of its matter would weigh billions of tons. These remnants are the ultimate survivors of the cosmic struggle, spinning rapidly in the dark and casting beams of radiation like celestial lighthouses. Yet, like the white dwarfs, they too are subject to the slow, relentless cooling of time. As we dwell on these remnants, the universe begins to feel like a great museum of past intensities. The white dwarfs and neutron stars are the artifacts of an era of light. In the current age, they are still relatively warm, contributing a faint glow to the galaxies they inhabit. But as the trillions of years pass, as the expansion of the universe continues to push everything further apart, these remnants will lose their heat. The white dwarfs will eventually cool so much that they become black dwarfs, cold, dark masses of diamond-like carbon that emit no light at all. These black dwarfs are theoretical, for the universe is not yet old enough for any to exist, but they are the destination toward which all average stars are traveling. They represent the final state of matter in a universe that has exhausted its ability to shine. The presence of these remnants emphasizes the inevitability of the long twilight. No matter how stable or brilliant a star may seem, it is bound by the laws of energy. The transition from a living star to a cooling remnant is a natural consequence of fuel consumption. It is the universe's way of tidying up, of consolidating its matter into the most stable forms possible. In this era, the vibrant, chaotic movements of gas and dust have settled. The remnants do not move with the frantic energy of youth. They drift in predictable, lonely orbits. The silence of a galaxy made of white dwarfs and neutron stars is a deep, profound silence. It is the peace that follows a great storm, a state of rest where all the work has been completed and only the memory of the light remains. As you reflect on this cooling, you can almost feel the temperature of the cosmos dropping. The energy that once drove the dynamic evolution of galaxies is dissipating, spreading thinner and thinner across the expanding vacuum. The white dwarfs and neutron stars are the last bastions of heat, the final points of warmth in a cooling room. They are cooling to absolute zero, a state of perfect stillness where all molecular motion ceases. This descent is not a frightening prospect, but a rhythmic conclusion. It is the universe finding its lowest energy state, a place of ultimate stability where no further changes can occur. The remnants are the anchors of this peace, the solid ground upon which the final history of the universe will be written. Beside these solid remnants lie the enigmatic black holes, which we will explore further in the journey. But even they contribute to this sense of a fading tapestry. The white dwarfs and neutron stars stand in stark contrast to the explosive beginnings of their parent stars, providing a sense of closure to the stellar narrative. They are the survivors, the ones who remain when the gas is gone and the fires are out. Their longevity is a comfort, a sign that even in a universe of constant change, there are things that endure. They carry the history of the stars within their dense structures, acting as the silent keepers of the cosmic record. In the final stages of the era of remnants, the universe will be a dark and quiet place. The stars will be gone, replaced by these cold, inert spheres of matter. But even in this darkness, there is a certain majesty. The remnants are made of the same atoms that once resided in the hearts of suns, the same atoms that now make up your own body. They are the final form of the stuff of life. The cooling of the white dwarfs and neutron stars is the final exhale of the cosmos, a slow release of energy that leads to a state of eternal equilibrium. We are the observers of this path, the ones who can see the beginning and understand the end. As we conclude this chapter on the cooling remnants, prepare for the deepening shadows. We have seen the birth of stars, the thinning of the gas, the long twilight of the red dwarfs, and now the quiet afterlife of the white dwarfs and neutron stars. The universe is settling into its final arrangements, finding the places where it will stay for the rest of eternity. The light is fading, the heat is dissipating, and the silence is growing. But in the presence of these ancient monuments, we find a sense of continuity, a realization that even in the dark, the universe is still whole, still stable, and still remarkably beautiful. In the deep, stretching silence of the far future, after the last of the red dwarfs have flickered out and the white dwarfs have cooled into dark, crystalline spheres, the universe enters an era dominated by the most enigmatic structures in existence. This chapter explores the long, final act of the black holes, the gravitational giants that once anchored galaxies and swallowed light itself. For eons, these dark titans seemed eternal, immune to the passage of time and the decay that claimed the stars. But even they are subject to the slow, rhythmic laws of the cosmos. As we drift through this chapter, we will witness the incredible process of Hawking radiation, the mechanism through which even the most powerful black holes eventually exhale their mass back into the void, marking the final stage of the universe's long transition toward total stillness. Imagine a black hole sitting in the absolute center of a dead galaxy. It is a region of space where gravity is so intense that nothing, not even light, can escape its pull. In the earlier ages of the universe, this black hole was a violent and active engine, consuming gas, dust, and entire stars in a brilliant display of energy. But now, in the distant future, there is nothing left to consume. The galaxy around it is empty and cold. The black hole remains, a perfect dark sphere again. A background of infinite shadow. To the casual observer, it would seem that this object will exist forever, a permanent scar on the fabric of space-time. However, according to the principles of quantum mechanics, the vacuum of space is not truly empty. It is a bubbling sea of virtual particles that constantly pop in and out of existence. When this happens at the very edge of a black hole, the event horizon, the balance is disturbed. This process, named after the physicist Stephen Hawking, is the key to the black hole's ultimate fate. Occasionally, one particle of a pair falls into the black hole, while the other escapes into space. To maintain the balance of energy, the black hole must give up a tiny fraction of its own mass to account for the particle that fled. This is a process of unimaginable slowness. For a black hole with the mass of our Sun, it would take far longer than the current age of the universe to lose even a fraction of its weight. But in the timeline we are now exploring, time is the one thing the universe has in abundance. Over trillions upon trillions of years, the black hole slowly, steadily evaporates. It is as if the Titan is breathing out, a long microscopic exhale that carries its essence away into the cold vacuum of space, one particle at a time. As the black hole loses mass, a strange and poetic phenomenon occurs. It begins to get warmer. In the world of black holes, the smaller you are, the more energy you radiate. A massive black hole at the center of a galaxy is incredibly cold, colder than the deepest reaches of space, but as it shrinks over eons of evaporation, its temperature slowly rises. The exhale becomes more frequent, the radiation more intense. This is the ultimate reversal of the stellar life cycle. While stars start hot and end cold, Black holes spend most of their lives in near absolute cold and end their journey in a final brilliant flash of heat. This final breath is the black hole's way of returning all the energy it has locked away for trillions of years back to the universe. It is a slow, rhythmic unraveling of the most concentrated matter in existence. Imagine the scale of time required for the largest black holes, the supermassive ones that weigh billions of times more than our Sun, to complete this process. We are talking numbers like 10 to the power of 100 years. It is a duration so vast that the human mind cannot truly visualize it. It is a forever that eventually comes to an end. During these long eons, the universe is almost completely dark. The only activity is the faint, ghostly glow of Hawking radiation coming from these scattered dark spheres. They are the last active engines in the cosmos, the final holdouts against the total equilibrium of the Big Freeze. They sit in their lonely corners of space, slowly whittling themselves away, until they are no longer the size of galaxies, but the size of stars, then planets, then grains of sand. As a black hole reaches the very end of its life, the process of evaporation accelerates into a frantic finale. In its final seconds, the black hole releases a burst of high-energy gamma rays and particles, a tiny explosion that marks its total disappearance from the fabric of reality. This is the final breath. In that moment, the last concentrated point of gravity in that region of space vanishes, and the matter that was once part of a star, a planet, or a nebula is finally scattered as thin radiation across the infinite void. The black hole, which once seemed like an inescapable prison, proves to be a temporary vessel. The debt to the universe is paid in full. The energy is returned, though it is spread so thin across the expanding space that it can never again gather to form anything new. The disappearance of the black holes marks the end of the era of matter. Once the last black hole has evaporated, there are no more large structures left in the universe. There are no more points of light, no more centers of gravity, and no more heat sources. The universe becomes a sea of stray photons and subatomic particles, drifting further and further apart as the expansion of space continues its relentless work. This transition is the ultimate conclusion to the complex story. The universe has moved from the hyperdense singularity of the Big Bang to a state of absolute diffusion. The black holes were the final guardians of structure, and their passing leaves the cosmos in a state of total, undisturbed uniformity. This vision of the final breath of black holes is one of profound tranquility. It suggests that nothing in our universe is truly lost. It is merely transformed and redistributed. The black holes act as the final recyclers, breaking down the remnants of the stellar age and releasing them back into the void. As you listen to the description of this slow evaporation, you can feel the rhythm of the cosmos slowing down to its final, most basic level. The frantic energy of the beginning has been replaced by a measured, patient release. The universe is not being destroyed. It is simply fading away, choosing to end its story with a quiet whisper rather than a loud cry. As we conclude this chapter, we stand at the threshold of the deepest dark. We have seen the stars fade, the remnants cool, and the black holes breathe their last. The universe is now prepared for its final state, the state of absolute zero and total stillness. Expansion has done its job, matter has done its work, and the energy has been spent. We are moving into a realm where time still passes but change no longer occurs. It is the peace of the Big Freeze, a state of rest that will last for the rest of eternity. The black holes have given us the final evidence of the universe's commitment to balance, showing us that even the strongest grip must eventually let go. In the quiet that follows the evaporation of the last black hole, the universe achieves a level of stillness that is perfect and absolute. There is no more noise, no more heat, and no more light. The long journey from the edge of the universe to the end of time has reached its peak of isolation. We rest in the knowledge that every atom and every photon has found its place in the infinite. The final breath has been taken and the cosmos is finally, truly at rest. In the wake of the black hole's final evaporation, the universe enters its most profound and enduring state, a period of ultimate tranquility known as the Big Freeze. This chapter explores the descent into absolute zero, the theoretical limit where all thermal motion ceases and the universe achieves a state of perfect, undisturbed rest. We have traveled through the eras of light, of remnants, and of dark titans, and now we arrive at the final destination of the cosmic journey. It is a realm where the energy that once fueled the brilliant engines of star formation has dissipated into the cold, infinite vacuum of space, leaving behind an expanse that is almost entirely static. As we drift through this chapter, we observe the final settling of the cosmic dust, a slow and rhythmic cooling that marks the true beginning of the universe's eternal sleep. To understand the descent into absolute zero, we must first reflect on the nature of heat itself. Throughout the history of the universe, heat has been the driver of change. It was the intense heat of the Big Bang that allowed matter to form. It was the heat within stellar cores that forged the elements, and it was the heat of radioactive decay that warmed the interiors of planets. But heat is not a permanent state. It is a form of energy that naturally moves from areas of high concentration to areas of low concentration. In an expanding universe, this means that heat is constantly being spread thinner and thinner. As the fabric of space stretches, the particles of matter and the waves of radiation are pulled apart, their energy diluted by the growing volume of the void. This is the basic law that dictates descent into the cold. Imagine the universe as a vast room that is slowly getting larger. In the center of the room there was once a roaring fire, but as the walls moved outward, the warmth of that fire stretched across an ever-widening area. Eventually, even the embers fade, and the air begins to match the chill of the shadows. Cosmic scale. This cooling has been happening since the beginning. The cosmic microwave background radiation, which was once thousands of degrees hot, has already cooled to just a few degrees above absolute zero. In the era we are now contemplating, even this faint afterglow has stretched into invisibility. The temperature of the cosmos continues to drop, moving closer and closer to that final limit where the last vibrations of matter come to a halt. Absolute zero is a state of zero thermal energy, a point where the movement of atoms, the tiny dances of protons and electrons, finally stops. While the laws of quantum mechanics suggest that a tiny bit of zero-point energy always remains for all practical purposes, the universe has become an ice palace of infinite proportions. In this state, there are no more chemical reactions, no more biological processes, and no more geological shifts. The planets, if they have not been destroyed by the deaths of their stars, are frozen solid to their very cores. The white dwarfs and neutron stars, having surrendered their last bits of warmth to the dark, are now cold, dark spheres, indistinguishable from the vacuum that surrounds them. It is a world of absolute stillness, a place where time continues to pass, but the hands of the clock no longer move anything forward. This chilling descent creates an environment where all active processes cease. With energy so thinly spread across the cosmos, the once brilliant engines of star formation no longer ignite. The universe sinks into a state of deep emptiness, a void that is not just empty of matter, but empty of potential. We often think of the dark as something heavy or oppressive, but in the context of the Big Freeze, the dark is simply the absence of struggle. It is the end of the conflict between gravity and pressure, between heat and cold. The universe has won its battle against entropy by finally achieving it. It has reached a state of maximum disorder in the most orderly way possible, by becoming completely uniform and completely still. In this quiet era, the universe appears almost static, a vast expanse where time continues, but no significant changes occur. The Big Freeze leaves behind only cold, inert matter slowly fading into a darkness that is absolute. If you were to drift through this future universe, you would see no light from distant galaxies, for they have long since crossed the cosmic horizon. You would see no flickering stars, for they have all gone out. You would find only the occasional lonely atom or photon traveling for trillions of light years without ever encountering another piece of matter. It is the ultimate expression of the isolation we discussed in earlier chapters. The universe has grown so large and so cold that every part of it is effectively alone in its own private infinity. As you listen to the description of this descent, you might feel a sense of weightlessness, as if the cold itself is a soft, numbing blanket. There is nothing left to do in this universe, no more work to be performed, and no more stories to be writ. 10. It is the final paragraph of the cosmic book. The cooling to absolute zero is the universe's way of ensuring that its rest is undisturbed. In a warmer universe, things are always moving, breaking, and reforming, but in the cold of the big freeze, everything is preserved in its final state. The universe becomes a photograph of its own conclusion, a perfect and unchanging image that will remain for the rest of eternity. This state of heat death is often portrayed as a bleak or tragic ending, but when viewed through the lens of the whispering scientist, it is the ultimate form of peace. It is the resolution of all tension. Throughout the billions of years of its existence, the universe has been a place of incredible violence, supernovae, black hole collisions, and the crushing pressure of gravity. Descent to absolute zero is the end of that violence. It is the moment when the universe finally lays its burdens and allows itself to be still. It is the deep, dreamless sleep that follows a very long and very busy day. As we reach the final stages of this cooling, we realize that the universe has completed its cycle. It has used its energy to create beauty, complexity, and life, and now it is returning to the simplicity from which it came. The atoms that once made up the stars and the people who wondered about them are now still, their long journey through the light finally over. The descent into absolute zero is not an event that happens suddenly. It is a slow and rhythmic fading, a gradual transition from the music of existence to the silence of the void. We are the ones who can imagine in this silence, the ones who can appreciate the scale of the rest that the universe has earned. In the quiet of this understanding, we find our own sense of peace. The vastness of the cold is not a void to be feared, but a space of ultimate stability. The universe is whole, even in its stillness. It is complete, even in its darkness. As we conclude this chapter on the descent into absolute zero, we prepare our minds for the final possibilities, the alternative ends, and the potential for rebirth. But for now, we rest in the cold. We drift in the absolute stillness of a universe that has finally found its equilibrium, a cosmos that is at last and forever perfectly still, in stark contrast to the slow, rhythmic decline of the big freeze. Another scenario envisions a far more dramatic and energetic end to the cosmic narrative, one that finds its roots in the mysterious force we have come to know as dark energy. This chapter explores the violent edge of our universe's potential destiny, the Big Rip. While our previous chapters have focused on the universe drifting into a peaceful, cooling sleep, the Big Rip presents a vision of a universe that eventually becomes too large for its own strength to hold together. It is a story of intensification, where the very fabric of space becomes so restless and so powerful that it begins to push back against the bonds of matter, leading to a systematic and inevitable dismantling of everything we have ever known. From the grandest galaxy clusters down to the smallest components of the atom. To understand this possibility, we must return to the concept of dark energy, that invisible influence that has been pushing the galaxies apart for billions of years. In most models of the universe, dark energy is thought to be a constant force, a steady background pressure that remains uniform as space expands. But what if dark energy is not constant? What if it is a phantom energy that grows more powerful as the universe gets larger? If the strength of dark energy increases over time, the rate of expansion will eventually reach a point of no return. In this scenario, the expansion does not just move distant galaxies away from view, it begins to act on a local scale, exerting a repulsive force that overcomes the gravitational glue, holding the universe's structures together. This is the beginning of the end, a progression that is systematic and relentless. Imagine a future billions of years from now where this intensification reaches a critical threshold. The first signs of the Big Rip would occur on the largest scales of the cosmos. Galactic clusters, those massive families of thousands of galaxies bound by gravity, would be the first to feel the strain. The space between the individual galaxies would begin to stretch with such force that the gravitational pull keeping them together would simply fail. The clusters would disintegrate, with galaxies drifting off into the void like seeds scattered by a strong wind. At this stage, a resident of a planet within one of these galaxies might not notice anything unusual in their local sky, but the distant, shimmering maps of the superclusters would begin to vanish, not because of distance, but because the structures themselves are being pulled apart. As the phantom energy continues to grow, the disintegration cascades down to smaller and smaller scales. Eventually, the expansion becomes strong enough to attack the integrity of individual galaxies. Our own Milky Way, a structure that has stood for billions of years, would find its spiral arms unraveling. The stars that have orbited the galactic center for eons would find the floor beneath them moving too fast for gravity to maintain their paths. One by one, the stars would be torn from their orbits, sent flying into the darkening expanse as lonely, isolated wanderers. The great celestial engine would fall silent, its components separated by the ever-growing hunger of space itself. This is the violent edge of expansion, where the fabric of reality becomes a predatory force actively seeking to isolate every piece of matter. The timeline then moves to our own solar system. As the Big Rip approaches its final stages, the force of expansion begins to overcome the gravity of the Sun. The planets, which have circled their parent star in a rhythmic ancient dance, would be pulled away from their orbits. Imagine the Earth, after billions of years of stability, being nudged further and further into the dark, not by a collision or a passing star, but by the very space it occupies. The Moon would drift away from the Earth, and the atmosphere would begin to thin as the gravitational hold of our world is compromised. It is a systematic dismantling of the architecture of life. The forces that once provided order and predictability are replaced by a singular, overwhelming urge to expand. In these final years, the sky would go truly dark, as even the nearest stars are pulled beyond the horizon of visibility. But the Big Rip does not stop at the level of stars and planets. Its power continues to scale down, entering the realm of the molecular and the atomic. In the final hours of the universe's existence, the repulsive force of space becomes stronger than the electromagnetic forces that hold molecules together. Objects would simply cease to be solid. Your home, the mountains, and even the water in the oceans would dissolve into a cloud of stray atoms as the bonds between them are snapped by the stretching of space-time. This is the point where the laws of physics, as we experience them on a human scale, are completely overwhelmed. There is no longer any stuff in the universe, there is only a frantic, high-speed dispersal of the components of matter. In the final minutes, the expansion reaches the atomic scale. The electrons that have orbited nuclei since the dawn of time are stripped away. Finally, in the last fraction of a second, the nuclear forces that hold the cores of atoms together are overcome. Protons and neutrons are torn into their constituent quarks. The universe becomes a sea of fundamental particles, each separated from the other by distances that grow at an infinite rate. This is the definitive conclusion to the cosmic narrative, a state where the expansion has become so violent that it has literally shredded the tapestry of reality. If the Big Freeze is a slow fading into a dreamless sleep, the Big Rip is the sudden tearing of the page, a cataclysmic event that leaves nothing intact and no memory of the structures that once were. Predictions suggest that if our current observations of accelerated expansion persist, and the dark energy is indeed of the phantom variety, this event could occur in approximately 22 billion years. While that is a vast duration compared to a human life, in the cosmic calendar, it is a relatively sudden end. It puts a definitive conclusion to the story of the universe, ensuring that no remnants are left to cool and no black holes are left to evaporate. The Big Rip is the ultimate expression of space's dominance over matter. It reminds us that we exist only because the forces of the universe are currently in a state of delicate balance, a balance that allows gravity to build while expansion remains gentle. As you listen to the description of this potential future, you might feel a sense of awe at the sheer power contained within the empty vacuum of space. The very air around us and the ground beneath us are held together by forces that are powerful, yet not infinite. The Big Rip is a reminder of the universe's capacity for drama. It is a story of a system that eventually overcomes its own limits. Yet, even in this violent vision, there is a rhythm. The progression from clusters to galaxies to stars to atoms is a logical and orderly sequence. It is the universe's final act of simplificati. On breaking everything down into its most basic parts before the expansion carries them into the ultimate dark. As we conclude this chapter, we rest in the knowledge that we live in the temperate age of the cosmos. The Big Rip is a distant possibility, a theoretical boundary at the edge of our understanding. For now, the stars remain in their orbits, and the atoms of our world remain tightly bound. We have explored the violent edge, but we are still safely within the heart of the story. The expansion is a quiet hum in the background, a gentle stretching that provides the room for us to exist and to wonder. We take a deep breath, grounding ourselves in the stability of the present as we prepare to look at another possibility, one where the universe decides to return to its beginnings rather than tear itself apart, as a thought-provoking counterpoint to the dramatic shredding of the Big Rip or the endless cooling of the Big Freeze. Another theoretical possibility suggests that the universe could eventually reverse its expansion altogether, choosing a path of return over a journey into oblivion. This chapter explores the pulse of renewal known as the Big Crunch, a scenario where the outward momentum of the cosmos is eventually overcome by the patient, inexorable pull of gravity. In this vision, the history of the universe is not a one-way trip into the dark, but a grand rhythmic cycle, a cosmic heart that beats over trillions of years. It is a story of a universe that decides to gather its scattered pieces and return to the singular point from which it began, potentially laying the groundwork for a new beginning, a new Big Bang that resets the entire narrative of existence. To understand the mechanics of the Big Crunch, we must imagine the universe as a grand projectile launched into the air. For billions of years, it has been flying upward, moving away from its origin endpoint with incredible speed. In the scenarios of the Big Freeze and the Big Rip, that projectile never stops. It either drifts forever or is torn apart. But in the Big Crunch, the gravity of the entire universe, the cumulative pull of every galaxy, every star, and every unseen particle of dark matter eventually acts as a tether. If the density of matter in the cosmos is high enough, there will come a moment of peak expansion, a silent turning point where the outward push finally tires. In that cosmic instant, the expansion stops. For a brief moment, the universe hangs in a state of perfect, breathless balance before it begins the long, slow fall back toward itself. The early stages of this contraction would be almost imperceptible to any civilizations watching the stars. The distant galaxies, which for eons had been shifting toward the red, would slowly begin to shift toward the blue. This blue shift is the signature of approach, the visual evidence that the gaps between the great islands of light are finally closing. First, it would be a peaceful transition. The universe would still be vast and cold, but the isolation we have discussed in previous chapters would begin to dissolve. The cosmic horizon would stop shrinking and start to expand once more, bringing long-lost galaxies back into view. It would be a time of cosmic reunion, where the structures that were once separated by billions of light-years begin to feel the presence of their neighbors. As the contraction gathers pace over millions of years, the mood of the universe undergoes a profound transformation. Instead of the thinning of matter we have observed, the cosmos begins to experience a cosmic crowding. The intergalactic gas that had been dispersed into the void is compressed, warming as it is squeezed into a smaller volume. The temperature of the space between galaxies begins to rise, while the current universe is cooled by its own growth. Its own collapse heats the contracting universe. The cosmic microwave background, which is now a cold whisper, would begin to gain energy, transforming back into a roar of radiation. The sky would slowly begin to brighten, not from the birth of new stars, but from the cumulative heat of all the light that has ever been emitted, trapped within a shrinking container. In the later stages of the Big Crunch, the environment becomes extreme. The galaxies begin to merge, not in the slow, graceful dances we see today, but in a frantic, high-energy collision of entire clusters. The stars themselves would find the space around them becoming dangerously hot. Eventually, the background temperature of space would exceed the temperature of the stars themselves, making it impossible for them to radiate their heat. The suns of the universe would begin to cook from the outside in, eventually dissolving back into a sea of plasma. This is the ultimate life cycle reversal we've studied. The complexity of planets, stars, and galaxies is systematically undone, reduced back to the raw, fundamental elements from which they were forged. The universe is shedding its structural layers, returning to a state of primal simplicity. As the universe approaches the final moments of the crunch, the contraction enters the realm of the ultra-dense. The entire mass of the billions of galaxies is squeezed into a volume no larger than our solar system, then a single star, and then a single atom. In these final stages, the laws of physics as we currently understand them begin to break down. Gravity becomes so intense that it curves space-time into a tight, impossible knot. We reach a point of extreme compression where quantum fluctuations and exotic effects dominate. This is the singularity, the mirror image of the Big Bang. But instead of being the end of the story, NY theorists believe this point of extreme density could trigger a big bounce. The compression might reach a physical limit, causing the universe to rebound and begin a new phase of expansion. This cyclical model of the universe presents a vision of endless renewal, where each phase of expansion and life is followed by a phase of contraction and rebirth. It suggests that our current universe is perhaps just one in an infinite series of cosmic pulses. The Big Crunch reminds us that the fate of the cosmos may not be a simple one-way journey into oblivion, but rather an intricate process with the potential for rebirth. It is a comforting thought, the idea that the universe is a self-sustaining system that breathes in and out over eons. In this view, the edge of the universe is not a physical wall or a cold death, but a turning point in a much larger dance. The matter that makes up your body and the stars above was once part of a previous cycle, and it will be part of the cycles to come. The beauty of Big Crunch is its symmetry. It provides a sense of closure that the other theories lack. It suggests that everything that was once scattered will be gathered back together, that every photon of light will return to the source, and that the silence of the end will eventually lead to the noise of a new beginning. While this scenario remains highly speculative and depends on the mysterious balance of dark energy and matter, it serves as a powerful reminder of the possibilities that lie beyond our current horizon. The universe is a place of deep mystery. Its ultimate destiny is a secret it keeps well, but whether it ends in ice, in fire, or in a pulse of renewal, it does so with a scale and a logic that is profoundly moving. As you reflect on this pulse of renewal, you can imagine the cosmic contraction as a slow rhythmic pull, like the tide returning to the shore. The dist. Answers are closing, the heat is returning, and the universe is coming home. There is no more isolation in this vision, only a gathering of them all. It is a state of ultimate togetherness. We rest in the stillness of the present, knowing that even if the universe were to one day choose the path of the crunch, it would be a journey of billions of years, a process so slow and so grand that it is indistinguishable from eternity. The stars are safe in their orbits, and the expansion continues its gentle work, but we carry the possibility of the return in our minds as a final, hopeful note in the cosmic symphony. In the silence that follows Big Crunch contemplation, we find ourselves back at the center of our own experience. We have traveled to the ends of time and seen the various ways the story might conclude. We've seen freeze, rip, and pulse. Through all these visions, the common thread is the incredible order and beauty of the physical laws that govern it all. The universe is a masterpiece of balance. As we conclude this chapter on the pulse of renewal, we prepare to bring our focus back to our own time and our own place, considering how these grand cosmic narratives reflect the immediate challenges and the enduring spirit of exploration that defines our own existence on this small blue planet. While the fate of the universe unfolds over trillions of years, the challenges facing our own planet are immediate and pressing, creating a poignant contrast between the grand cosmic narrative and the fragile timeline of human history. This chapter explores the relationship between the vast, slow decline of the heavens and the rapid, transformative changes happening here on Earth. As we have seen, the universe moves through its stages with a measured grace. Stars ignite, galaxies drift, and space expands over eons that dwarf our comprehension. Yet, when we turn the mirror toward ourselves, we see a story that is moving at a frantic pace. The grand cosmic narrative, filled with distant cataclysms and the eventual evaporation of black holes, stands in sharp contrast to the immediate crises of climate change, technological shifts, and the survival of our species. In this reflection, we find that while we are insignificant in scale compared to the cosmic eraser, our choices today are the most critical elements of our own timeline. Imagine standing on the surface of the Earth, looking up at the ancient light of a star that is billions of years old. In that moment, you are experiencing two different speeds of time. The star is a relic of a process that takes billions of years to conclude, while you are a participant in a civilization that can change its entire destiny in a single century. This is the mirror of time. We are the bridge between the eternal and the ephemeral. The same scientific inquiry that allows us to calculate the distance to the great attractor also guides our efforts in understanding the delicate balance of our own atmosphere. We are a part of the cosmos that has become self-aware, a small yet curious element in a chronology that stretches far beyond everyday life. This awareness brings with it a dual responsibility to mitigate the immediate risks to our home while also considering the long-term consequences of our actions within the larger cosmic landscape. The challenges of our current era, climate change, pandemics, and the potential for technological catastrophe, define the future of human civilization on timescales we can directly experience. These issues are immediate and visceral, yet they are guided by the same physical laws that govern the stars. Our planet's carbon cycle is a smaller, faster version of the chemical cycles that take place within a galaxy. The energy that powers our cities is a harnessed fragment of the nuclear fires that light the sun. When we address these Earth-scale challenges, we are essentially practicing for our role as a cosmic species. We are learning how to manage a closed system, how to preserve the conditions for life, and how to look ahead toward an uncertain horizon. This serves as a simple reminder that while the universe is vast and its evolution spans eons, the choices we make today have an immediate impact on the future of life on our home planet. History is filled with examples of problems and phenomena that were entirely unforeseen in their time. In the year 1900, many of the threats we face today were unimaginable. The idea of a global digital network, the splitting of the atom, or the warming of the entire planet's climate would have seemed like far-fetched science fiction. Likewise, in the coming decades, challenges and opportunities may arise that we cannot yet conceive. These unknown unknowns serve as a powerful reminder that our understanding of the universe and our own existence remains incomplete. The story of the cosmos is not merely a tale of predetermined outcomes, it is an ongoing dialogue between observation, theory, and an ever-shifting landscape of possibilities. By staying open to the unexpected, we remain resilient, whether we are refining our models of cosmic evolution or developing new policies to address global resource management. The spirit of exploration must remain alive. As we dwell on this mirror, we realize that the universe's long-term fate and Earth's immediate future are interconnected through the lens of human knowledge. We study the Big Rip and the Big Crunch, not because they will happen tomorrow, but because they tell us something about the nature of the reality we inhabit right now. Understanding the limits of light and the expansion of space humbles us, reminding us that we are guests in a very large and very old house. This humility is a vital tool for our survival. It encourages us to value the now, to protect the vibrant, active world we still have, and to appreciate the rare moment of stability we occupy in the cosmic timeline. We are living in a window of time where the stars are bright, the air is breathable, and the mysteries of the universe are solvable. This is our golden hour. The contrast between the cosmic eraser and the human pen is profound. The universe may eventually thin out into a cold, dark void, but that process is so distant that it provides a background of stability rather than a source of fear. It is the Earth-scale challenges that require our urgent focus. Yet, The perspective we gain from looking at the stars is what gives us the motivation to solve our problems here. If we are the only minds capable of witnessing the long twilight of the red dwarfs or the evaporation of black holes, then our survival becomes a cosmic necessity. We are the storytellers of the universe. If we fail to address our immediate risks, the story of the cosmos remains unread, a magnificent play with no audience. Therefore, environmental protection and global resource management are not just political or social issues. They are acts of cosmic preservation. Think of the silence of the moon compared to the vibrant noise of a city. That contrast is a microcosm of the universe. Most of the space is quiet, cold, and inert. Life is the exception. It is the spark of high-energy activity in a world moving toward equilibrium. By protecting our planet, we are protecting the universe's most complex and interesting experiment. We are the active part of the cosmic narrative, the ones who are still forming new connections and discovering new laws, while the rest of the universe begins its long, slow settlement. This realization helps us navigate the anxiety of the modern world. When we feel overwhelmed by the pace of change on Earth, we can look to the stars for a sense of permanence and scale. And when we feel insignificant in the face of the cosmic void, we can look to our own achievements and our potential to change our future. The time mirror reminds us that we are not separate from the universe. We are its products and its observers. The atoms in our telescopes were forged in the same stellar nurseries we discussed in earlier chapters. The electrical signals in our brains follow the same quantum rules as the particles at the edge of a black hole. By solving the problems of today, we are ensuring that the spirit of exploration continues into the distant future. We are making sure that there will always be someone to watch the light change and to record the thinning of the gas. Our immediate survival is the first step in a journey that could eventually take us far beyond the edge of our own solar system. As we conclude this reflection on Earth and the cosmos, we find a sense of renewed purpose. The grand scale of the universe does not make our lives meaningless, it makes them miraculous. We are the small, curious elements in a chronology that stretches across eons, yet we have the power to shape the next 100 years of our own world. We rest in the quiet of this balance, appreciating the vastness of the heavens while focusing on the needs of the earth beneath our feet. The stars will continue their slow expansion, and we will continue our rapid evolution, moving forward with a dual approach of wonder and responsibility. The speed of light is one of the most fascinating and mysterious concepts in the universe, serving as the ultimate cosmic speed limit beyond which nothing with mass can ever travel. As we transition from the grand fate of galaxies to the fundamental laws that govern the very movement of information and matter, we encounter a boundary that defines the structure of our reality. It is a constant, a shimmering line in the sand drawn by the laws of physics, ensuring that the universe remains an orderly place where cause always precedes effect. In this chapter, we explore the fascinating world of the speed of light and the profound implications it has for our journey through the unknown. While it may seem like an insurmountable barrier, understanding why this limit exists allows us to unlock a deeper appreciation for the fabric of space and time itself, preparing us to explore the limits of what is truly possible in the universe. To begin this exploration, we must first recall what speed actually represents in the grand scheme of physics. We call speed a certain value equal to the distance an object travels in a certain time, often without a specific direction. In our daily experience, moving faster simply requires more effort or more fuel. However, as an object approaches significant fractions of the speed of light, the rules of the world change in ways that defy our common sense. When an object moves, it does not just gain velocity, it also increases its level of kinetic energy and, most importantly, its relativistic mass. The faster an object moves, the more mass it effectively gains, and consequently, the more energy is required to accelerate it even further. This is why a space rocket moving at incredible speeds would cause a far greater scale of destruction if it collided with a meteorite than a slower one. The energy consumed and stored within that motion is immense. For objects that have mass, reaching the speed of light would require an infinite amount of energy, a physical impossibility in a finite universe. But what about particles that have no mass, like photons? This is where the story of light becomes truly magical. Light is an electromagnetic wave resulting from the emission of energy from heated bodies perceived by our eyes as the vibrant colors of the world. Yet light is also a stream of massless particles called photons or quanta. Because they possess no mass, photons are not burdened by the weight of acceleration. They are born moving at the maximum speed possible. In a cosmic vacuum, light travels at approximately 186,000 miles per second. This is the likely speed limit for the entire universe, a fundamental constant that Albert Einstein used to change our entire understanding of reality through his work on general relativity. Einstein's main idea was that gravity is not just a force acting between objects, but a curvature of space itself, and that the laws of physics, including the constant speed of light, apply equally everywhere. According to the principles of general relativity, light is constant, meaning it always travels at the same speed regardless of the observer's motion. The reason light can achieve this absolute velocity is twofold: the absence of mass in photons, and the fact that light does not move along the timeline in the same way we do. To visualize this, we look to the parabolic model of Hermann Minkowski, Einstein's teacher, who proposed that time and space are not separate entities, but are unified into a four-dimensional fabric called space-time. In this model, our universe has three spatial dimensions: height, width, and depth, and one temporal dimension. Everything in the universe is interconnected within this fabric. Depending on your location and your movement through space-time, you interact with space and time differently, a concept that leads us to the heart of why light is so unique. Imagine this using a simple coordinate system. If you are sitting perfectly still, perhaps watching a video or listening to a story, you are moving only in time. Your position in space does not change, and your spatial speed is zero, yet you are still hurtling through the dimension of time at a steady rate. However, if you decide to get up and walk toward a window, you begin to move in both time and space. Because the total speed through space-time is constant for all things, the more you move through space, the slower you must move through time. This is the phenomenon known as time dilation. It was famously proven in 1971 when scientists placed highly accurate hydrogen clocks on airplanes and flew them around the world. When the planes landed, the clocks that had been moving through space were running slower than the clocks that stayed on the ground by about 1/1,000,000th of a second. Light, however, represents the extreme end of this balance. Light moves only in space. It does not feel the influence of time at all. If we could put a clock on a photon, the hands of that clock would appear to be suspended forever. Because light has no mass, it is also not affected by gravity in the traditional sense of being pulled like a stone. However, because gravity curves the very fabric of space, light must follow those curves. If a beam of light passes near a massive body like a black hole or a star, it follows the geodesic lines of the warped space-time. Its path may curve, and its energy may be shifted, but its local speed remains the same constant value. This brings us back to the question of whether we, as beings with mass, can ever achieve or exceed this speed. We are already moving at the speed of light in a sense, but our speed is scattered between the dimensions of time and space. Because we have mass, time affects us, and we are anchored to the timeline. Even the most powerful particle accelerators, which use electromagnetic fields to push subatomic particles to incredible velocities, can only reach 99.99% of the speed of light. That final fraction of a percent remains forever out of reach, guarded by the requirement for infinite energy. Yet, the history of science is filled with observations that seem to challenge this limit. At the end of the 20th century, astronomers observed phenomena that appeared to move faster than light, such as the jets of ionized matter ejected from the center of the galaxy M87. These beams of plasma seemed to be traveling at several times the speed of light, a phenomenon called superluminal motion. However, deeper analysis revealed this to be an optical illusion caused by the geometry of the jet's orientation toward Earth. The photons emitted later in the jet's path have a shorter distance to travel to reach us, making it appear as though the matter is outrunning its own light. While these illusions are breathtaking, They ultimately reinforce the fact that the light constant remains the unbreakable law of the vacuum. There are, however, natural processes that can accelerate particles to near-light speeds through magnetic explosions. When magnetic fields in space collide and become entangled, they can snap and break apart, throwing charged particles away at ultra-high speeds. This process acts as a natural particle accelerator. Yet even here, the speed of light is the ceiling. It is only when light travels through a medium, such as water or glass, that its speed is slowed down by interactions with molecules. In these environments, it is actually possible for other particles to move faster than the local speed of light in that medium. This creates a haunting blue glow known as Cherenkov radiation, a celestial version of a sonic boom. This radiation is a reminder that while the vacuum speed limit is absolute, the interaction between matter and light is full of nuances and hidden beauty. As we contemplate the cosmic speed limit, we realize that it is not just a barrier but a protect, or of causality. If we could travel faster than light, we could theoretically arrive at a destination before we even left, creating logical paradoxes that would unravel the consistency of our history. The speed of light ensures that the story of the universe remains coherent, that every cause has an effect, and that every moment is connected to the next in a logical sequence. We are passengers on a journey through time and space, moving at a pace that allows us to experience the world with clarity. The constant nature of light provides a foundation for our understanding of the stars, allowing us to look back into the past and map the distances of the void with certainty. In the quiet reflection of this chapter, we find peace in the limits of our reality. The speed of light defines the boundaries of our observable universe, creating a horizon that keeps the cosmos manageable for our minds. It is the heartbeat of physics, a steady and unchanging rhythm that governs the movement of every photon and every atom. While we may never physically outrun the light, we have the capacity to understand it, to harness it, and to use it as a bridge to the furthest reaches of space. We rest in the stability of this law, knowing that the light will always find its way to us at the same reliable pace, carrying the secrets of the universe across the vast, expanding dark. Building upon the foundational laws of the cosmic speed limit, we now venture into the speculative and exhilarating realm where science begins to flirt with the boundaries of the impossible. This chapter explores the concept of the Alcubierre drive, more commonly known as the warp drive, and the mysterious requirement of negative energy. While the laws of special relativity forbid an object with mass from accelerating through space at the speed of light, they do not technically forbid space itself from moving or expanding. At any speed it chooses. It sounds like the plot of a fantastic dream, yet scientists are seriously considering the mechanics of how we might bend the very fabric of the universe to travel to distant stars in the blink of an eye. By stretching the canvas of space into a wave, we could hypothetically compress the area in front of a ship and expand the area behind it, allowing the vessel to sit within a stationary bubble while the universe itself does the moving. To understand the warp bubble, imagine a surfer riding a wave. The surfer is not necessarily swimming faster than the water, they are simply being carried by a localized distortion of the ocean's surface. In this cosmic analogy, the Alcubierre drive consists of three distinct parts. First, there is the inner bubble, a protected passenger space where the travelers reside. Within this sanctuary, time passes at a normal rate, or perhaps even more slowly, shielded from the violent distortions occurring outside. The second and third parts are the outer shells of the bubble, where the real physics of warping takes place. One side of the shell uses an immense amount of energy to contract space-time, pulling the destination toward the ship. The other side uses an equal force to expand space-time, pushing the starting point away. This creates a so-called warp bubble that can effectively move across the cosmos at speeds that appear to surpass light, without ever violating Einstein's rule that no local object can outrun a photon. However, implementing such a drive faces a monumental hurdle, the necessity of negative energy. According to the general theory of relativity, all forms of matter and energy we encounter in our daily lives possess positive mass and positive energy. They exert a gravitational pull that draws things together. Negative energy, on the other hand, would possess a repulsive gravitational quality, act as the inflation needed to expand the space-time fabric behind the ship. While negative energy is a theoretical necessity for a stable warp bubble, it is notoriously difficult to find. General relativity suggests it might be impossible on a large scale, yet quantum theory offers a glimmer of hope. In the microscopic world of subatomic particles, small quantities of negative energy have been observed in phenomena like the Casimir effect, where two uncharged plates in a vacuum experience a tiny force pushing them together due to the exclusion of certain vacuum fluctuations. One of the main problems with this theory is the sheer scale of energy required to manifest a warp bubble large enough for a spacecraft. Early estimates suggested we would need the energy equivalent of an entire planet's mass to create a single bubble. This staggering requirement has led modern astrophysicists to seek more efficient methods. In 2021, researcher Eric Lentz developed a concept that might allow for warp travel using only positive energy sources. His model suggests that instead of a simple bubble, a specific configuration of liquid plasma with a huge mass, perhaps 10% of the energy of our Sun, combined with precisely shaped electromagnetic fields, could create a soliton, a self-reinforcing wave of space-time. This wave could transport a ship at speeds close to the light constant. While this model moves us closer to a reality where negative energy is not required, it still leaves us at the mercy of the cosmic speed limit. These positive energy waves may not be capable of accelerating to the superluminal speeds of a true Alcubierre drive. As we dwell on the mechanics of these bubbles, we must also consider the strange consequences of traveling in such a manner. If a warp drive were ever perfected, it would effectively be a form of time travel, because the ship is bypassing the traditional constraints of the light constant. Observers at different points in the universe would see the ship's journey in different chronological orders. This brings us back to the classic causal paradoxes where a traveler could potentially arrive at their destination before they ever left their home. Some physicists, like Sabine Hossenfelder, suggest that these paradoxes might be avoided if we look at them through the lens of general relativity rather than special relativity. If a ship moves along with the matter of the universe in the same direction of time, it might preserve the causal relationship, ensuring that the history of the cosmos remains a logical and unbroken chain. The pursuit of the warp drive is more than just a search for speed, it is a search for a way to bridge the isolation of the universe. As we have discussed in previous chapters, the expansion of space is constantly pulling the stars away from us. Without a method to shortcut these distances, the vast majority of the universe will remain forever out of reach. The warp bubble represents our desire to stay connected to the cosmic whole, to be more than just observers of ancient light. It is a testament to human ingenuity that we are even capable of theorizing about the manipulation of the space-time metric. Even if we never build a warp ship, the study of these concepts helps us refine our understanding of gravity, energy, and the limits of what a civilization can achieve. Imagine the silence of a ship inside such a bubble. While the universe outside is being shredded and rebuilt by the distortion of the drive, the passengers within would experience a state of perfect stillness. They would be the eye of the storm, moving through the void with a grace that defies the laws of the past. This vision of travel is inherently soothing because it suggests that we are not trapped by the distances of dark. It offers the hope that the thinning of cosmic matter is not a permanent barrier, but a challenge to be overcome. The dark energy that pushes the galaxies apart could, in theory, be harnessed to bring us closer to the stars. So far, it remains impossible to confirm whether a warp drive can exist without negative energy, and we are nowhere near starting experimental work on such a device. The technical knowledge required to manipulate plasma at such a massive scale and to shape electromagnetic fields into diamond-like patterns is far beyond our current capabilities. Yet, the history of science has shown us that the impossible of one century often becomes the engineering of the next. By studying the Alcubierre drive, We are laying the intellectual groundwork for a future where we might truly become a spacefaring species. We are identifying the problems, defining the energy requirements, and exploring the paradoxes before we even take our first step. In the quiet reflection of this chapter, we rest in the wonder of the what-if. The idea of the warp bubble is a beautiful marriage of mathematics and imagination. It takes the cold, hard facts of Einstein's relativity and finds a loophole that allows for the spirit of exploration to thrive. Whether the universe allows for such a shortcut remains to be seen, but the very fact that we can conceive of it is a sign of our progress. We are no longer just looking at the stars, we are thinking about how to touch them. The negative energy we seek may be hidden in the quantum foam, waiting for a future generation to uncover its secrets and use it to inflate the first bubble that will carry us toward the horizon. As we conclude our exploration of warp bubbles, we carry with us a sense of expanded possibility. We have looked at the limit, and then we have looked at the ways to step around it. The universe is a vast and complex puzzle, and the warp drive is one of the most intriguing pieces we have found so far. We move forward now to look at other shortcuts the universe might provide, natural tunnels in the fabric of space that might allow us to travel millions of light-years without the need for a ship-made bubble. The story of our journey through the unknown is getting deeper, and the silence of if the warp bubble is a vehicle that carries us across the waves of the cosmos, then the Einstein-Rosen bridge is a hidden doorway, a shortcut through the very foundation of the universe that bypasses the need for distance altogether. In this chapter, we explore the theoretical tunnels in space commonly known as wormholes. These structures represent a different kind of mastery over the cosmic speed limit, suggesting that 2 points in the universe, separated by millions of light-years of expanding dark, could be connected by a narrow passage that allows for nearly instantaneous travel. It is a concept that challenges our perception of the universe as a flat, predictable surface, and invites us to see it as a complex, folded fabric, where the shortest distance between 2 points is not a straight line, but a bridge. As we sink into the quiet of this exploration, we will trace the history of these bridges from their mathematical birth in the mind of Albert Einstein to their current status as a tantalizing yet elusive possibility for the future of exploration. Imagine a large, flat sheet of paper. On one side of the sheet, draw a small circle to represent our home galaxy. On the opposite side, draw another to represent a distant star system. In the traditional sense, to travel from one to the other, you must move across the entire length of the paper, following the slow and steady pace of the light constant. But now, imagine folding that paper in half so that the 2 circles are positioned directly on top of one another. If you were to poke a needle through both layers, you would create a hole that connects them directly. This is the essence of an Einstein-Rosen bridge. It is a topological feature of space-time that links distant regions of the universe through a higher dimensional tunnel. Instead of traveling through the space between the stars, a traveler would move through the bridge itself, effectively stepping out of one part of the universe and immediately entering another. The idea first emerged in 1935 when Einstein and his colleague Nathan Rosen were examining the equations of general relativity. They discovered that mathematics allowed for a specific kind of singularity that could act as a bridge. While black holes were seen as bottomless pits from which nothing could escape, these bridges were envisioned as a way for space-time to curve so sharply that it created a tunnel. In those early days, these structures were purely theoretical, a mathematical quirk of a universe that was much more flexible than anyone had previously imagined. They suggested a cosmos that was not just a vast, empty container, but a living, breathing fabric that could be pinched, folded, and connected in ways that defy our daily intuition. For decades, the Einstein-Rosen bridge remained a fascinating footnote in the study of gravity, a ghost in the machine of the heavens. However, as our understanding of physics evolved, so did the complexity of these tunnels. While the original Einstein-Rosen bridges were mathematically possible, they were also fundamentally unstable. According to the classical equations, a wormhole would pinch shut the very instant anything, even a single photon of light, tried to pass through it. Gravity, which creates the bridge in the first place, also acts to collapse it. To keep such a tunnel open long enough for a person or a ship to pass through, one would need a form of exotic matter or negative energy, similar to what is required for a warp drive. This negative energy would act as a structural support, pushing the walls of the tunnel outward and preventing the gravitational collapse. Without this invisible scaffolding, the bridge would disappear back into the quantum foam before it could ever be used, leaving no trace of its existence. This brings us to the great challenge of finding or creating these bridges. Unlike stars or galaxies, wormholes do not emit light and do not leave obvious signatures in the sky. They are the ultimate hidden paths. Some scientists believe that microscopic wormholes might be popping in and out of existence all around us at the smallest scales of reality, part of the quantum foam that makes up the vacuum. If we could find a way to stabilize and enlarge these tiny fluctuations, we might be able to create our own bridges. Others suggest that naturally occurring wormholes might have been created during the high-energy chaos of the Big Bang, stretched to cosmic proportions by the same inflation that created the galaxies. These ancient tunnels might still be hidden in the dark, connecting the corners of the universe like secret veins in the body of the cosmos. But even if we were to find a stable wormhole, the journey through it would be unlike anything we can imagine. A traveler would not experience the passage of time or distance in the way we do on Earth. The bridge would be a region where the laws of space and time are compressed and distorted. Entering the mouth of the wormhole would feel like being drawn into a sphere of shimmering, distorted light, a lens that shows a warped view of the destination on the other side. Inside the tunnel, the familiar stars would vanish, replaced by the exotic geometry of the bridge itself. Then, in a moment that feels both eternal and instantaneous, the traveler would emerge into a completely different part of the universe, perhaps millions of light years from where they started. It is the ultimate expression of the universe's interconnectedness. The potential of these bridges extends beyond mere distance. Because space and time are unified in the fabric of the cosmos, a wormhole that connects 2 points in space might also connect 2 points in time. This has led to the fascinating and often confusing possibility of time travel through Einstein-Rosen bridges. If one mouth of a wormhole were moved at relativistic speeds while the other remained stationary, a time difference would develop between the two ends. A traveler could then enter our one end and emerge in the past or the future. While this leads to the same logical paradoxes we have discussed with warp drives, it reinforces the idea that the universe is a place of deep, untapped potential. The bridges are a reminder that our perspective limits our current understanding of now and here as beings who move slowly through a three-dimensional world. As we reflect on these tunnels, we can feel the vastness of the universe becoming a little more intimate. The Einstein-Rosen bridge suggests that we are never truly as isolated as we seem, even as the expansion of the universe pulls the galaxies apart. The fabric of space-time may still be stitched together by these hidden connections. They are the shortcuts that make a vast universe feel like a single, cohesive home. To contemplate the wormhole is to find comfort in the idea that there is always a way back, always a path that leads through the dark to a place of light. It is a vision of a universe that is not just expanding, but is also deeply and intricately woven. Currently, we have no proof that wormholes exist, nor do we have the technology to create the negative energy needed to stabilize them. They remain on the frontier of theoretical physics, a beautiful possibility that awaits further discovery. Yet, the search for these bridges continues to drive our understanding of the most extreme environments in the universe. By studying how gravity behaves at its limits, we are slowly uncovering the rules that might one day allow us to build our own doorways. We are learning to speak the language of the fabric of reality, preparing ourselves for a time when the distances between the stars are no longer barriers, but merely invitations to travel. In the quiet of this chapter, we rest in the image of the cosmic bridge. We imagine a universe where the dark is not an empty void, but a canvas filled with hidden paths and secret doorways. The Einstein-Rosen bridge is the ultimate symbol of human curiosity, the desire to find a way through the impossible and to connect with the furthest reaches of the unknown. We are the architects of these theories, those who dream of tunnels in the sky, as we move forward to look at how information itself might travel through these strange connections, we carry with us the hope that the universe is far more accessible than it appears, and that the silence of the void is merely a veil waiting to be lifted. Finally, as we move beyond the physical tunnels of space and the stretching bubbles of gravity, we arrive at the most mysterious and intimate connection of all, a phenomenon that Einstein famously dismissed as spooky action at a distance. This chapter explores the inseparable dance of quantum entanglement, a fundamental property of the universe where two particles become so deeply linked that the state of one instantly influences the state of the other, regardless of how many millions of light-years of expanding void lie between them. While our previous chapters have focused on the movement of matter and the bending of space, quantum entanglement offers a glimpse into a hidden layer of reality where distance itself seems to lose its meaning. It is a world of pure information and instantaneous harmony, providing a hypothetical way to communicate across the vast reaches of the cosmos, at speeds that would make the light constant seem like a crawl. Imagine two tiny particles, perhaps a pair of electrons or photons, born from the same energetic event. In the quantum world, these particles do not have fixed identities until they are measured instead. They exist in a hazy cloud of possibilities. When they become entangled, their fates are woven together into a single, shared existence. You could take one of these particles and leave it here on Earth, while carrying the other to the very edge of the observable universe, past the red dwarfs and the cooling white dwarfs we have visited in our minds. If you were to measure the spin of the particle here on Earth, the distant particle would instantly settle into the corresponding state. There is no signal traveling between them, no beam of light crossing the dark, and no delay in time. They simply act as one. This is the inseparable dance, a rhythm that exists beneath the surface of space-time, suggesting that the universe is far more interconnected than its vast distances would lead us to believe. This phenomenon is a cornerstone of quantum mechanics, a field that describes the universe at its most basic level. In this realm, the certainties of classical physics are replaced by the elegance of probability and variability. Entangled particles communicate by changing their state, such as their spin or their energy level, in a way that is perfectly synchronized. This has led to the fascinating concept of FTL, or faster-than-light communication. Imagine an astronaut on a journey to a distant exoplanet, hundreds of light-years away. In a world with quantum communication, they could send a signal back to the controller on Earth almost instantly. The data would not have to struggle against the expansion of space or wait for years to cross the vacuum. It would simply appear, a ghostly echo of the astronaut's discovery, shared across the stars in a heartbeat. However, as we delve deeper into this dance, we encounter a fundamental problem that keeps this concept in the realm of the hypothetical. The main challenge is the inherent randomness of the quantum world. While the two particles are perfectly synchronized, we cannot force a particle into a specific state to transmit a particular piece of data without breaking the entanglement. If we try to manipulate the particle T, say yes or no, the delicate connection snaps, and the results become random once again. It is a cruel paradox of nature. The connection is absolute and instantaneous, yet the information we wish to send remains elusive. The particles are like two dancers who always mirror each other's movements perfectly, but neither can be told what move to make next. Because of this, current quantum mechanics suggests that information cannot be transmitted at a speed greater than the light constant, preserving the causality of the universe even at the subatomic scale. Despite these limitations, the study of entanglement is an important step toward a deeper investigation of the light constant and the nature of spacetime. It tells us that the universe possesses a non-local character, meaning that points in space that appear separate to us are actually part of a unified whole. This realization is profoundly soothing. It suggests that even as the expansion of the universe pulls galaxies apart and creates vast celestial voids, there is a level of reality where everything remains in touch. The isolation we have feared in previous chapters is, in a way, an illusion of our scale. At the quantum level, the universe never truly lets go. The dance continues in the dark, a silent and invisible web of connections that spans the entirety of existence. As you reflect on this inseparable dance, you can imagine the billions of entangled pairs that must exist throughout the cosmos. Every star that ignites, every black hole that evaporates, and every atom that drifts in the void is part of this quantum tapestry. We are living in a universe that is constantly talking to itself in a language we are only just beginning to decode. The randomness that currently prevents us from sending messages across the stars may one day be understood as a different kind of order, a higher form of logic that we have yet to master. The technical knowledge we gain from studying quantum entanglement is not just about communication. It is about understanding the very fabric of being. It is the study of how the one becomes the many and how the many remain the one. In the distant future, our priority will be to develop the technical knowledge we have so that our main goal in the study of space-time will be speed and connectivity. We are looking for ways to bridge the gaps, to overcome the thinning of matter, and to stay present in a universe that is trying to drift apart. Quantum entanglement provides the blueprint for that future. It is the ultimate bridge, more subtle than a wormhole and more direct than a warp bubble. It represents the pinnacle of cosmic integration. As we conclude this chapter, we rest in the quiet beauty of this connection. We imagine the particles spinning in perfect harmony across the light years, a silent testament to the fact that nothing in the universe is ever truly alone. The dance of the quanta is a reminder that the universe is a place of infinite complexity and hidden grace. It is a story of harmony in the face of vast distances. Even as the big freeze approaches and the stars cool to absolute zero, the entangled pairs will still be there, mirroring each other in the dark. We are the observers of this dance, the ones who have noticed the rhythm and are trying to learn the steps. By understanding entanglement, we are bringing ourselves closer to the heart of the mystery, moving from the scale of galaxies to the scale of the infinitesimal, and finding that the same sense of wonder exists in both. We are now nearing the end of our journey through the unknown. We have seen the beginning and the end, the speed limits and the shortcuts, the heat of the nurseries and the cold of the freeze. We have explored the ways we might one day travel and communicate ACR. Os the expanding dark. All that remains is to look at one final mystery, a gravitational anchor that sits behind the veil of our own galaxy, pulling us toward an uncertain future. The inseparable dance of the quanta has prepared us for this final revelation, showing us that the universe is a place of attraction and connection, where even the most invisible forces can shape the destiny of everything that exists. In our final step through the vast, expanding corridors of the cosmos, we return to our own celestial neighborhood to confront a mystery that sits behind the glittering veil of the Milky Way. This chapter explores the phenomenon that has intrigued and puzzled scientists for years, hidden in the region of space we call the avoidance zone. Here there exists a gravitational anomaly so vast and so powerful that it tugs at the very fabric of our universe, acting as the final shore toward which we are all drifting. This is the great attractor. Although invisible to our traditional telescopes, its gravitational influence is so immense that it affects the motion of galaxies hundreds of millions of light-years away, including our own. As we conclude our journey, we will delve into the impact of this anomaly and the challenges we face in observing such an elusive region, ultimately finding a sense of peace in the grand, interconnected movement of the stars. Imagine for a moment that you are floating down a river in a small boat without oars. The water is calm and the current is gentle but absolute. No matter how much you might wish to stay in one place, the river carries you forward toward a destination you cannot yet see. Our Milky Way is that boat, and the great attractor is the unseen bend in the river that determines our path and our speed. About 4 decades ago, astronomers using the world's most sensitive instruments began to notice something strange. They discovered that our galaxy is traveling through space much faster than the general expansion of the universe should allow. We are hurtling through the void at 2,500 times the cruising speed of a commercial airliner, a velocity so great that it defies our understanding of a simple, uniform expansion. This net motion suggested that something massive was pulling us, a hidden concentration of matter that Alan Dressler famously named the Great Attractor. The mystery of this attraction is deepened by its location. It sits directly behind the dense disk of our own galaxy, obscured by the thick clouds of dust and the billions of stars that make up the Milky Way. This region, known as the zone of avoidance, is like a curtain drawn across a window, preventing us from seeing what lies on the other side. Still, gravity is unmistakable. It affects a region of space spanning hundreds of millions of light years, encompassing our local group and the larger Laniakea supercluster. This mass consists not only of visible matter like stars and galaxies, but also of dark matter, that invisible and mysterious substance that makes up the majority of the universe's mass. Understanding the Great Attractor is like putting together a cosmic puzzle where the most important pieces are hidden in the shadows, leaving us to infer the shape of the whole from the movement of the parts we can see. To peek behind this veil, astronomers have had to become creative, using radio and infrared waves that can pass through the dust of our galaxy like a torch illuminating a dark room. One of the primary methods used is observing the 21-centimeter neutral hydrogen line, a faint signal that can be detected by radio receivers. In the late 90s, surveys using instruments like the Parkes multi-beam receiver in New South Wales began to reveal thousands of previously hidden galaxies. These observed ions allowed scientists to confirm that the Great Attractor is not a single monstrous entity, but a region of space with a higher concentration of mass, centered within the Norma cluster. This cluster is one of the most saturated known regions of galaxies, a dense urban center in the cosmic landscape toward which everything in our vicinity is currently migrating at an astounding speed. As we dwell on this movement, we must consider the discovery of even larger structures, such as the South Pole Wall. This recently identified veil of galaxy dust and gas extends for at least 700 million light-years, a structure so massive that it disrupts the local expansion of the universe. Like the Great Attractor, it remains partially hidden, stretching across the southern sky from Perseus to Apius. These structures are all interconnected, forming a vast cosmic web where the motion of one part influences the whole. Our galaxy is part of a grand, flowing river of matter, guided by the gravitational pull of these massive anchors. It is a reminder that even in the vast isolation of the expanding universe, we are still bound by the ancient laws of attraction. We are moving toward a final shore, a center of gravity that defines our place in the grand scheme of the cosmos. But as we contemplate this journey, a burning question remains: will the Great Attractor eventually swallow us up? In the earlier chapters of our story, we looked at the violent possibilities of the Big Rip and the cold silence of the Big Freeze. In contrast, the Great Attractor represents a local struggle against those universal ends. However, the answer provided by modern science is reassuring. Despite its enormous pull, the Great Attractor is not a cosmic monster waiting to consume us. As the universe continues to expand, and as that expansion accelerates due to dark energy, the gravitational bonds holding these superclusters together will eventually weaken. In the very distant future, the expansion of space will likely overcome the pull of the attractor. The galaxies that are currently drifting toward this central mass may eventually find themselves moving away once more, as the river of space itself grows too wide and too fast for the current of gravity to maintain its hold. The future of the universe is a vast, ever-expanding cosmic sea. The Great Attractor is a formidable anchor that will eventually lose its power. The superclusters may disintegrate, and the massive structures we are currently mapping will fade into the isolation of the Big Freeze. This realization brings our journey to a quiet and reflective conclusion. We have seen the evolution of space measurements, the birth and death of stars, the limits of light, and the various ways the universe might find its end. We have seen that we are small, yet we are capable of understanding the largest scales of reality. The Great Attractor is the final mystery in our local narrative, a sign that the universe is still full of surprises hidden just behind the next curtain of stars. As you rest in the knowledge of these grand movements, you can feel the rhythm of the cosmos as a steady, guiding force. We are not lost in the dark, we are part of a systematic and beautiful progression. The study of the great attractor, the South Pole Wall, and the cosmic web is an ongoing dialogue between human curiosity and the vastness of the unknown. Even if our telescopes can never see every corner of the avoidance zone, our minds can grasp the logic of the pull. We are the explorers of light, those who have learned to read history written in time and gravity. The universe is a masterpiece of balance, and we are its witnesses, standing on the shore of our own little island of stars, watching the tide of expansion and the current of action play out over the eons. In the final moments of this exploration, the vastness of the universe becomes a comfort. The time and distance scales are so large they provide a sense of ultimate stability. The stars will continue to glow, the space will continue to stretch, and the great attractor will continue its silent tug for billions of years to come. We have found our place in the chronology, a moment of brilliant clarity where we can look both backward to the beginning and forward to the end. The silence of the void is not an empty silence, but a full one, resonant with the echoes of everything we have learned. We are home in the cosmos, moving with the current, and resting in the peace of a universe that is both infinite in its reach and intimate in its connections. As the light of this story begins to fade, we settle into the quiet of our own world. We have traveled from the edge of the universe to the heart of our own supercluster, finding that the same laws of physics and the same spirit of wonder apply everywhere. The journey of the whispering scientist is a circle, returning us to the ground beneath our feet with a new appreciation for the sky above. The expansion is gentle, the stars are steady, and the dark is a soft blanket that covers the mysteries we have yet to solve. We close our eyes to the rhythmic pulse of the universe, drifting off into a dreamless sleep, carried by the invisible currents of a cosmos that is and always will be a wonder to behold. Our journey through the stars has reached its end, but the story of the universe continues in the silence of the night. Sleep now, knowing that the great engines of the heavens are in perfect order, and that you are a part of a narrative that will never truly end. The stars are watching, the void is waiting, and the peace of the cosmos is yours.